Since the dawn of civilization, Earth's moon has been one of the first celestial bodies to awaken fascination and mystery. Long before the invention of writing or the development of modern science, ancient peoples already looked to the night sky and saw in that bright solitary body a guide, a marker of time and a symbol of divine power. It controlled the tides, illuminated dark nights, and influenced myths, religions, and calendars. The first agricultural societies depended on lunar cycles to organize their harvests, and many cultures associated the moon with gods and goddesses, interpreting its phases as supernatural signs. This deep bond between humanity and the moon turned it into one of the most enduring symbols in human history, long before we knew it was just one among hundreds of moons orbiting other worlds in the solar system. With the invention of the telescope by Galileo Galilei in the early 17th century, the human gaze gained a new dimension. Galileo not only observed the irregular surface of our moon, full of mountains and craters, but also made one of the most revolutionary discoveries in the history of astronomy. When pointing his telescope at Jupiter, he identified 4 luminous points moving around the planet. They were Io, Europa, Ganymede, and Callisto, the Galilean moons. For the first time, humankind proved that not all celestial bodies revolved around Earth, challenging the geocentric view that had dominated for centuries. This moment not only paved the way for the consolidation of Copernicus's heliocentric model, but also marked the beginning of the science of moons, revealing that ours was not unique. From that point on, human curiosity expanded. New, more powerful and precise telescopes revealed moons orbiting Saturn, Uranus, and Neptune. Each discovery confirmed that the solar system was much more complex and dynamic than we imagined. Over the centuries, scientists began mapping these moons, distinguishing the large and geologically active ones from the small and rocky ones, often captured from the Kuiper Belt region or formed from collisions. Today we know there are more than 290 confirmed moons orbiting the planets of the solar system, not counting dozens of bodies still under study that may join this list in the future. Each of them has unique characteristics, holding valuable clues about the formation and evolution of our planetary system. The fascination that began with Earth's moon has transformed into a quest for universal understanding. Today, moons are not only seen as astronomical curiosities, but also as natural laboratories capable of revealing profound mysteries: how planets formed, how icy environments may sustain underground oceans, and even whether life could flourish in worlds very different from our own. With each discovery, human perception expands, and the idea that the moon was solitary dissolves before the reality of a cosmos populated by countless satellites, each with its own story and potential to transform our vision of the universe. In astronomy, the term moon is used to designate any natural body that orbits a planet or a dwarf planet. Although our own moon is the most familiar, and for a long time seemed unique, the truth is that it represents only one example within a vast population of natural satellites scattered throughout the solar system. These bodies differ enormously in size, composition, origin, and orbital characteristics. There are giant moons such as Ganymede, which is larger than the planet Mercury, and there are tiny moons only a few kilometers in diameter that resemble captured asteroids more than actual worlds. This diversity makes moons fundamental objects for understanding cosmic history and the evolution of planetary systems. The modern definition of a moon was established starting in the 17th century after the discoveries of Galileo around Jupiter and Christian Huygens around Saturn. Since then, the classification of moons has taken into account their origin and orbital behavior. Some formed at the same time as their planets, from the same disk of gas and dust that gave rise to the solar system. Others, like Triton around Neptune, seem to have been captured later, probably originating from outer regions such as the Kuiper Belt. There are also moons resulting from catastrophic collisions, such as our own moon, whose origin is attributed to the impact of a Mars-sized object with the primitive Earth billions of years ago. This range of possibilities shows that moons are living records of different cosmic processes. As for the number of known moons, it has grown continuously as observational technology advanced. At the beginning of the 20th century, only a few dozen were known. Today, with more powerful ground-based telescopes and space probes dedicated to planetary exploration, we already count more than 290 confirmed moons orbiting the 8 planets of the solar system. Jupiter and Saturn host the majority, with more than 90 each, due to their enormous gravitational fields capable of capturing small bodies. Uranus has about 27 confirmed moons, Neptune 14, Mars 2, and Earth only 1. Mercury and Venus have no known moons, which intrigues astronomers and sparks debates about the reasons for this absence. The classification of moons also considers their composition and geological activity. Some, like Io, show intense volcanism and remain geologically active. Others, like Enceladus and Europa, hide liquid oceans beneath icy crusts, attracting strong astrobiological interest. Many of the smaller moons, however, are inert, covered with craters and showing no signs of internal activity. This diversity shows that even within the same planetary orbit, there are worlds with extremely distinct characteristics. This reinforces the importance of studying them individually, rather than treating them as simple secondary satellites. The study of moons has gained even more relevance in recent decades because these bodies can answer central questions of planetary science. They help explain how planets formed, how gravity shapes complex systems, and even which environments may be capable of sustaining life. Thus, when we speak of moons, we are not merely describing cold rocks in space, but rather complete worlds with their own histories and, in some cases, surprising potential to harbor organisms. By establishing this broad and scientific concept, astronomy allows us to look beyond the familiarity of our moon and see a vast archipelago of worlds orbiting the giants of the solar system. The study of the moons of the solar system was only made possible thanks to the continuous evolution of observational techniques. In the early 17th century, Galileo Galilei pointed his rudimentary telescope at Jupiter and recorded the existence of 4 small points of light orbiting the planet. This simple discovery, made with a low-power instrument, revolutionized astronomy. The telescope revealed not only the Galilean moons, but also the idea that bodies could orbit other planets, definitively breaking the notion that everything revolved around Earth. This moment is considered the inaugural milestone of systematic observation of moons in the cosmos. With advances in optics and the construction of larger telescopes, astronomers began identifying new moons around Saturn, Uranus, and Neptune. In the 19th century, refracting telescopes and later reflecting telescopes enabled clearer observations, allowing the recording of satellites such as Titania, Oberon, and Triton. These discoveries required not only good equipment, but also patience and precision, since many moons were faint and blended with the stellar background. Even so, the perseverance of dedicated astronomers expanded the list of known bodies, building the foundation for modern planetary astronomy. In the 20th century, the observation of moons took a giant leap forward with the arrival of astronomical photography and later radio astronomy. The ability to capture long-exposure images allowed the detection of very small satellites or those with eccentric orbits. Photographic analysis also made it possible to measure the trajectories of these bodies with greater precision. However, the true revolution would come with the space age. In 1959, the Soviet probe Luna 2 impacted the surface of Earth's moon, inaugurating direct exploration. A few years later, missions such as Voyager 1 and 2 transformed our knowledge of the moons of the gas giants, revealing complex and active surfaces that had once been only points of light. Modern techniques rely on a combination of advanced ground-based telescopes, space observatories, and planetary probes. Instruments such as the Hubble Space Telescope and the recently launched James Webb capture images in different wavelengths, enabling the analysis of atmospheres, chemical compositions, and even plumes of ice on satellites such as Enceladus. The Cassini-Huygens mission at Saturn and Galileo at Jupiter produced high-resolution images, as well as collected data on magnetic fields, internal heat, and gravitational interactions. These missions radically changed the view of moons such as Triton, Europa, and Enceladus, elevating them to the category of potential havens for extraterrestrial life. Today, observational methods include spectroscopy, radar, gravity measurements, and even the detection of particles emitted by plumes. These tools provide detailed information without the need to land directly on celestial bodies. Furthermore, the observation of occultations, when a moon passes in front of a distant star, allows very precise measurements of the size and atmosphere of these objects. Sophisticated computer simulations also help in understanding orbital dynamics and the interior of these moons, combining data obtained from different missions. Thanks to this combination of technological innovation, scientific dedication, and pioneering missions, moons have ceased to be just bright points around distant planets and have become worlds full of enigmas, active geology, complex atmospheres, and, in some cases, promising conditions for life. Each advance in observational techniques brings us closer to answers to some of humanity's greatest questions. Are we alone in the universe, and if not, on which of these moons might the answer be hidden? Mars, the so-called red planet, has only two small moons, Phobos and Deimos. Although tiny compared to the moons of the gas giants, their discovery and study represent important milestones in astronomy. They were identified in 1877 by American astronomer Asaph Hall using the telescope at the United States Naval Observatory in Washington. After nights of careful observation, Hall managed to record the two bodies in orbit around Mars, becoming the first to reveal to the world that the neighboring planet also possessed satellites. This discovery was received with enthusiasm, as until then it was believed that Mars was solitary, like Mercury and Venus. Since then, Phobos and Deimos have become objects of great scientific interest, both for their characteristics and for their mysterious origins. Phobos, the larger of the two moons, has a diameter of about 22 kilometers, while Deimos is even smaller, at approximately 12 kilometers. Both have irregular shapes resembling asteroids more than spherical bodies. Their surfaces are covered with impact craters, indicating billions of years of collisions with small space fragments. Gravity on their surfaces is extremely low, meaning a human could make huge leaps effortlessly. This aspect makes them very different from our moon, reinforcing the idea that they did not form alongside Mars, but were probably captured by the planet's gravity after originating in the asteroid belt region. The capture hypothesis, however, raises questions. Deimos's orbit is almost circular and aligned with Mars's equator, which would be unusual for a captured body. Phobos, on the other hand, orbits very close to Mars, only about 6,000 kilometers above its surface, making it the closest moon to its planet in the entire solar system. This proximity causes Phobos to complete a revolution around Mars in just 7 hours and 39 minutes, faster than the planet's own rotation. This phenomenon creates a dramatic future. In a few tens of millions of years, Phobos will be destroyed by Mars's gravitational forces, breaking into fragments that may form a temporary ring around the planet. Another theory suggests that Phobos and Deimos are not captured asteroids, but rather fragments resulting from a colossal impact that struck Mars in the distant past. In this scenario, the collision would have ejected debris into orbit, which later clumped together and gave rise to the two moons. This hypothesis is reinforced by some similarities between the surface composition of these bodies and the Martian crust. However, the evidence is still inconclusive, and the question of their origin remains open. A detailed study of their composition and interior may provide stronger answers. Phobos and Deimos also arouse practical interest for space exploration. Due to their low gravity, they are considered potential support points for future human missions to Mars. An outpost on Phobos, for example, could serve as a platform for sending probes, vehicles, and even astronauts to the Martian surface with lower energy costs. Furthermore, direct exploration of these moons may reveal not only secrets about Mars, but also clues about the evolution of the inner solar system. Missions are already being planned to land and collect samples, such as the MMX, Martian Moons Exploration Mission, led by the Japanese Space Agency, which aims to bring material from Phobos back to Earth for analysis. Despite their small size, Phobos and Deimos play an essential role in understanding cosmic history. They represent not only silent companions of Mars, but also fundamental pieces in the puzzle of planetary formation and in the search for strategies of interplanetary exploration. By studying them, science is not merely examining two small blocks of rock in space, but preserved witnesses of the processes that shaped the solar system since its infancy. Since the discovery of Phobos and Deimos in 1877, these small Martian moons have sparked astronomers' curiosity, but it was only with the arrival of the space age that it became possible to study them directly. The first major approach took place in the 1970s with the Soviet Phobos-Target program missions, which aimed to observe and eventually land on Phobos. Although technical problems limited the full success of these missions, they provided unprecedented images and basic data about the size, orbit, and irregular surface of the two Martian moons. During the same period, the American Mariner 9 Dutch and Aus and Vikinger probes also captured images of Phobos and Deimos, revealing details of craters, grooves, and surfaces covered with dust and loose regolith. These first portraits changed perceptions of these bodies, showing that although tiny, they had their own geological histories. In the following decades, new probes once again focused cameras and instruments on these moons. The Mars Global Surveyor, 1996-2006, and the Mars Express, launched by the European Space Agency in 2003, were especially important. Mars Express remains active and has conducted several close flybys of Phobos, capturing images with resolutions of only a few meters. These data made it possible to map the moon's surface with unprecedented precision and to measure its gravitational field, helping to understand its internal structure. The evidence suggests that Phobos may be a porous body, composed of rock and ice fragments loosely bound together, strengthening the hypothesis that its origin may be related to impact debris or a captured asteroid. Despite these advances, many mysteries still surround Phobos and Deimos. What is their true origin? Are they captured asteroids or fragments of Mars? What is their exact composition? And how might they contribute to future crewed missions to the Red Planet? To answer these questions, new missions are being planned. The most promising project is MMX, Martian Moons Exploration, led by the Japanese Aerospace Exploration Agency, JAXA. Scheduled to launch later this decade, the mission's main goal will be to land on Phobos, collect soil samples, and bring them back to Earth. It will be the first time that fragments of a Martian moon will be studied in terrestrial laboratories, which could provide definitive answers about their composition and origin. In addition to MMX, other proposals are being discussed within the scientific community. NASA and ESA have already studied plans to send orbital probes and even landers to Phobos and Deimos, focusing both on scientific research and on preparing for future human missions. Interest in using these moons as intermediate platforms for Martian exploration is growing. Instead of landing directly on Mars, which requires enormous amounts of energy and complex logistics, astronauts could use Phobos as a base of operations. From there, it would be possible to control robots on the Martian surface in real time, explore the moon for resources such as frozen water, and, in the future, establish a permanent forward outpost. The study of Mars's moons may also have practical implications for Earth's protection. Understanding the structure and composition of small bodies, similar to asteroids, helps prepare strategies for defense against possible future impacts. In this sense, Phobos and Deimos serve as natural laboratories, nearby, accessible, and extremely valuable for planetary science. Each new mission directed at these bodies not only answers old questions, but also opens doors to future applications that go far beyond Mars. These small moons, once considered mere astronomical curiosities, are now at the center of ambitious plans involving science, technology, and human exploration. By investigating them, we take an essential step toward understanding Mars in depth, while at the same time moving closer to the era in which humanity will become a multiplanetary species, able to use space not only as an object of study, but as an active territory for survival and expansion. In the early 17th century, in January 1610, Galileo Galilei made one of the most transformative observations in the history of science. Using a telescope with an aperture of only a few centimeters, he pointed the instrument toward Jupiter, the largest planet in the solar system. By repeatedly observing the planet for several nights, he noticed 4 small luminous points that changed position in relation to it. At first he thought they might be nearby stars, but he soon realized that these points orbited Jupiter in a regular manner. Thus Galileo discovered the planet's 4 largest satellites, Io, Europa, Ganymede, and Callisto, which we now call the Galilean moons in his honor. This discovery, recorded in his work Sidereus Nuncius, published in March of the same year, not only revolutionized astronomy but also triggered a profound shift in the worldview of that era. The importance of this observation goes beyond the simple identification of new celestial bodies. Until then, the dominant cosmology was the geocentric model, defended by Ptolemy and supported by the Church. according to which Earth was the immutable center of the universe. The fact that Galileo proved that bodies could orbit another planet weakened this conception and strengthened Copernicus's heliocentric model, which placed the Sun at the center of the solar system. This paradigm shift was one of humanity's greatest intellectual revolutions, and Jupiter's moons became irrefutable evidence that the cosmos was far more vast and complex than previously imagined. Each of these moons displayed unique characteristics that intrigued scientists from the start. Io, the closest to Jupiter, soon revealed itself as an extremely active body with signs of intense geological activity. Europa drew attention with its smooth and bright surface, suggesting the presence of ice. Ganymede impressed with its colossal size, even larger than the planet Mercury, while Callisto, the farthest, appeared as a relic of the past, covered in ancient craters. Although Galileo could not see these details, his discovery paved the way for centuries of observation, culminating in space missions that confirmed the richness of these worlds. The cultural impact of this discovery was so great that it extended beyond science. Philosophers, religious authorities, and thinkers of the time debated intensely about the implications of the finding. The idea that not all celestial bodies revolved around Earth shook age-old certainties and called into question established authorities. For challenging these conceptions, Galileo faced persecution and trial by the Inquisition, but his discovery remained one of the cornerstones of modern knowledge. The Galilean moons thus became symbols of the transition from medieval thought to modern science. Today, more than 4 centuries later, Io, Europa, Ganymede, and Callisto continue to be the focus of intense study, not only as historical witnesses of a scientific revolution, but also as fascinating worlds in their own right. They represent natural laboratories that help us understand everything from planetary formation processes to the conditions that may sustain life. Galileo's vision, limited by a rudimentary instrument, opened the doors to modern exploration, which now uses space telescopes, probes, and high-tech missions to investigate these 4 giant satellites in detail. By recalling this foundational moment, we can understand how a simple nighttime observation forever changed our perception of the universe and Earth's place within it. Among the 4 moons discovered by Galileo, Io stands out as one of the most fascinating and extreme bodies in the entire solar system. Located only 421,000 kilometers from Jupiter, it is the 3rd largest Galilean moon and, surprisingly, the most volcanically active object known. Its surface is a constantly changing landscape, filled with immense calderas, rivers of lava, and eruptions that can hurl material hundreds of kilometers high. Unlike our moon, whose craters have remained virtually unchanged for billions of years, Io is a living world where the terrain is continuously and dramatically renewed. This ceaseless activity makes Io a true natural laboratory for understanding geological processes on scales that surpass everything we know on Earth. The explanation for such intensity is directly linked to Jupiter's colossal gravity. Io is locked in a complex orbital dance with Europa and Ganymede, known as orbital resonance. This dynamic balance causes its orbit to be constantly stretched and compressed, resulting in a phenomenon called tidal heating. Jupiter's gravitational force literally stretches and deforms Io's interior, generating enough heat to melt large portions of its mantle and fuel unprecedented volcanism. In other words, the gas giant's gravity functions like an invisible furnace, keeping Io in geological boiling motion. Io's surface reflects this activity. Vibrant colors in shades of yellow, red, orange, and white cover the moon, the result of sulfur and sulfur dioxide compounds released during eruptions. Some of the largest calderas reach hundreds of kilometers in diameter, dimensions far greater than the largest terrestrial volcanoes. Among the most impressive phenomena are volcanic plumes, colossal jets of gas and particles that can rise up to 500 kilometers above the surface. These events were documented by the Voyager 1 probe in 1979, completely surprising scientists at the time, who had not expected to find such intense activity on a body seemingly small and distant. Since then, missions such as Galileo, New Horizons, and Juno have continued to reveal extraordinary details about Io. Observations show that the moon possesses a metallic core, possibly similar to Earth's, surrounded by a mantle heated by tidal forces. This heat drives constant volcanism, but also creates challenges for direct study of its surface, since landing on such an unstable world is an extremely complex task. Even so, Io is considered one of the most important bodies for planetary science because it illustrates how gravity can shape entire worlds and generate intense activity without depending on solar energy. Although Io is not regarded as a promising candidate for life, precisely because of its hostile sulfur-dominated surface, it plays a crucial role in Jupiter's system. Its eruptions release enormous amounts of particles that interact with the planet's magnetic field, creating intense auroras and feeding the so-called Io plasma torus, a gigantic cloud of electrically charged particles that encircles Jupiter. Thus, Io is not only shaped by the gas giant, but also directly influences it, demonstrating the interdependence between planet and satellite. In summary, Io represents the extreme of planetary geology, a world in constant transformation where invisible forces deform its interior and fuel volcanoes that surpass anything ever seen on Earth. It is a powerful reminder that the solar system harbors realities far beyond our everyday experience, revealing landscapes so violent and intense they seem to belong more to a work of fiction than to the real cosmos. Among all the moons of the solar system, few arouse as much scientific interest as Europa, the fourth largest moon of Jupiter. Discovered by Galileo Galilei in 1610, Europa initially appeared to be just a point of light among the stars, but centuries of observation and decades of space missions have revealed that beneath its icy surface there may exist a vast ocean of liquid water, making it one of the most promising candidates in the search for extraterrestrial life. Unlike Io, marked by explosive volcanism, Europa presents a calmer and more uniform face at first glance, but hides in its depths one of the most intriguing environments in the entire solar system. Europa's surface is composed of a thick layer of water ice, marked by immense cracks, fissures, and linear patterns stretching for thousands of kilometers. Interestingly, it has relatively few craters, suggesting that its crust is constantly renewing itself, erasing ancient scars. This phenomenon indicates that the moon is geologically active, not through volcanism like Io, but through processes linked to the dynamics of its underground ocean. The ice moves, breaks, and refreezes, creating a surface that resembles a slow-moving puzzle. This feature is significant because it suggests that beneath the ice there may be a liquid ocean kept warm by the same mechanism that powers Io, tidal heating caused by Jupiter's colossal gravity. It is estimated that Europa's ocean may be between 60 and 150 kilometers deep, covering the entire globe beneath the frozen layer. This means that Europa may contain more water than all of Earth's oceans combined. The presence of a global ocean protected by ice makes this environment particularly interesting for astrobiology. This is because liquid water, combined with energy sources from the moon's interior and with possible dissolved minerals from the ocean floor, creates conditions reminiscent of extreme ecosystems found on Earth, such as hydrothermal vents in the deep oceans. In these places on our planet, life thrives without sunlight, sustained solely by chemical reactions between water and rocks. If something similar occurs on Europa, the possibility that microscopic organisms inhabit its waters cannot be dismissed. The first strong evidence of this underground ocean came from the Voyager missions and later from the Galileo probe, which orbited Jupiter between 1995 and 2003. Galileo's instruments detected variations in the local magnetic field, consistent with the presence of a conductive, salty water layer beneath the surface. In addition, detailed images showed plumes and patches suggesting the presence of material coming from below, transported up to the crust. More recently, the Hubble Space Telescope recorded signs of water vapor plumes being ejected into space, similar to those observed on Enceladus, a moon of Saturn. These discoveries further increased the enthusiasm of the scientific community, as they indicate that direct samples of Europa's ocean may be launched into space, accessible without the need to drill through its thick ice crust. Europa is not only a priority target of scientific exploration, but also one of the most anticipated destinations of future space missions. NASA is developing the Europa Clipper mission, scheduled to launch this decade. This probe will carry out repeated flybys over the moon, measuring its surface magnetic field and composition with advanced instruments. The goal is to confirm the extent of the ocean, identify areas where the ice is thinner, and analyze the water plumes to search for signs of organic compounds. At the same time, the European Space Agency is planning the JUICE, Jupiter Icy Moons Explorers mission, which will study not only Europa, but also Ganymede and Callisto, broadening our understanding of Jupiter's icy moons. The study of Europa goes beyond scientific curiosity. If we confirm that its underground ocean harbors forms of life, even if only simple microorganisms, this will radically change our understanding of the universe. Life would no longer be an exclusive phenomenon of Earth, but something potentially common in environments with water and energy, even far from the Sun. Europa, with its hidden ocean beneath the ice, represents the hope that we are not alone and that life can flourish in unimaginable places. It is therefore more than a moon. It is a window into the future of astrobiology and into the answer to one of humanity's oldest questions. Ganymede is a true colossus among the moons of the solar system. With a diameter of 5,268 kilometers, it is larger than the planet Mercury and almost the size of Mars, placing it in a special category, not only as a satellite, but as a complete world in itself. Discovered by Galileo Galilei in 1610, along with Io, Europa and Callisto, Ganymede soon became a source of fascination due to its impressive size, but its importance is not limited to its dimensions. Modern observations have revealed that it is also the only known moon to possess its own magnetic field, as well as strong evidence of subsurface oceans. These factors make Ganymede one of the main targets of current planetary exploration. The surface of Ganymede presents a mixture of ancient cratered regions, similar to our own moon, with younger grooved areas marked by fracture patterns. These formations suggest intense tectonic activity in the past, which reshaped parts of the terrain. This duality makes Ganymede a kind of geological archive, recording both cosmic impact processes and internal phenomena that deformed its crust. Water ice is the main component of its surface, mixed with rocky silicates. In some locations, bright patches can be observed, indicative of relatively fresh ice, renewed by internal processes. The great enigma, however, lies within. Data from the Galileo mission showed that Ganymede possesses a metallic core, probably composed of iron and nickel, which generates a stable magnetic field. This sets it apart from all other known moons, making it more similar to planets such as Earth and Mercury. This magnetic field interacts with Jupiter's powerful magnetosphere, creating unique auroras that telescopes can detect. Furthermore, measurements indicate the existence of a vast layer of salty subsurface water, perhaps organized into multiple stacked oceans between layers of ice. This environment, shielded from radiation and warmed by internal forces, may contain the necessary conditions to support microscopic life. It is estimated that Ganymede harbors more water than all of Earth's oceans combined. This gigantic volume, combined with a stable and protected environment, makes it one of the main candidates for astrobiological studies. Although the thickness of the icy crust makes direct access to these oceans difficult, the mere fact of their existence already revolutionizes the scientific perspective on where life can emerge. It is no longer just the habitable zone around stars that defines the chances of life, but also the presence of internal heat and liquid reservoirs protected beneath ice. Space missions have played a fundamental role in revealing these mysteries. The Voyager probes in the 1970s and 1980s provided the first detailed portraits of Ganymede, showing its surface diversity. Later, the Galileo mission confirmed the presence of the magnetic field and strengthened evidence of oceans. Today, attention is focused on the JUICE, Jupiter Icy Moons Explorer, mission from the European Space Agency, which is expected to arrive at the Jovian system in 2031. JUICE will conduct long-term observations of Ganymede, including an exclusive orbital flyby, something unprecedented for any moon beyond our own. Its goal will be to map its surface, analyze its magnetic field, and investigate its internal structure in search of definitive evidence of subsurface oceans. Ganymede, therefore, is not only the largest moon of the solar system, but also a world full of enigmas and scientific potential. It shows us that natural satellites can be as complex as planets, with metallic cores, tectonism, deep oceans, and magnetic interactions. By studying it, humanity is not only expanding knowledge about Jupiter, but also exploring an alternative model of habitability. If life exists on Ganymede, even in microscopic form, it would confirm that biology can flourish in environments very different from Earth, completely redefining our search for life in the universe. Callisto, the second largest moon of Jupiter and the third largest in the entire solar system, is an enigmatic world that seems to preserve on its surface an almost intact memory of the cosmic past. With a diameter of 4,821 kilometers, it is only slightly smaller than Mercury, but much less dense, since it is composed largely of ice mixed with rock. Discovered by Galileo Galilei in 1610, Callisto soon stood out for its appearance, an ancient crust densely covered with impact craters, making it the most cratered body known in the solar system. Unlike Io, Europa, and Ganymede, Callisto shows no clear signs of recent geological activity, being considered a geologically dead world. Even so, beneath this frozen crust, a subsurface ocean may exist, opening the door to discussions about its astrobiological potential. The surface of Callisto is like a fossil record of the early solar system. It preserves craters that date back billions of years, some with colossal diameters, formed by violent impacts that go back to the time of planetary formation. Among these structures, the Valhalla Basin stands out, an impact ring almost 4,000 kilometers across, the largest ever observed on any body in the solar system. Another notable structure is the Asgard Basin, also formed by an ancient and massive impact. These striking features show that Callisto was exposed to intense cosmic bombardment, acting as a natural archive that preserves clues about the chaotic conditions of the planet-forming era. For a long time, scientists believed Callisto was just an inert frozen block, but recent missions have raised the possibility that beneath its crust lies a salty, liquid ocean. Observations by the Galileo probe between 1996 and 2003 detected variations in the Moon's magnetic field that can only be explained by the presence of a conductive layer beneath the surface. This result suggests the existence of liquid water mixed with salts, possibly located more than 100 kilometers deep. If confirmed, this discovery places Callisto among the moons with astrobiological potential, although less promising than Europa or Enceladus, due to the extreme depth and lack of significant internal energy. Even without major geological activity, Callisto offers unique advantages compared to Jupiter's other moons. Because it is located farther from the planet, it suffers less from the intense radiation of Jupiter's magnetosphere. This means that future manned missions could, in theory, establish bases on Callisto with fewer risks to astronauts. Furthermore, its low gravity and abundance of ice could provide useful resources for space exploration, such as water and rocket fuel. Thus, Callisto may not only be a scientific target of interest, but also a strategic candidate to serve as logistical support for human exploration of the Jovian system. Callisto's astrobiological potential is still debated. If a subsurface ocean does exist, it is possible that primitive microorganisms could survive in its depths, fed by chemical interactions between water and rock at the ocean floor. However, the absence of significant internal heat makes these chances lower than in Europa, where tidal activity provides constant energy. Still, the possibility of life cannot be entirely ruled out, and investigating Callisto may bring valuable clues about the diversity of environments where biology can emerge. In summary, Callisto is a world that bears on its surface the scars of the solar system's most ancient past, while potentially hiding liquid secrets in its depths. It is at once a time capsule and a potential astrobiological laboratory. Studying Callisto is like opening a book of cosmic memories, where each crater tells the story of violent eras, but whose interior may yet reveal an unexpected chapter, the persistence of liquid water and, perhaps, life beyond Earth. Beyond the four imposing Galilean moons, Jupiter harbors a true collection of smaller satellites that transform the Jovian system into a cosmic archipelago of extraordinary diversity. So far, more than 90 moons orbiting the gas giant have been confirmed, and most of them belong to this category of small irregular satellites, unlike Io, Europa, Ganymede, and Callisto, which formed from the same disk of gas and dust that gave birth to Jupiter. Many of these moons appear to have been gravitationally captured, probably originating from the asteroid belt or even more distant regions, such as the Kuiper belt. Their eccentric, inclined, and in some cases retrograde orbits, that is, moving in the opposite direction to the planet's rotation, reinforce the idea that they were not born alongside the giant, but were trapped by its colossal gravity. These moons are generally very small, ranging from just a few kilometers to a few dozen kilometers in diameter. Many of them resemble asteroids in their irregular shapes and cratered surfaces. Among the most studied groups are the so-called retrograde moons, divided into families that probably resulted from the fragmentation of larger bodies after collisions. Notable examples include the Ananke, Pasiphae, and Carm groups, which share similar orbital characteristics and seem to be the remnants of ancient captured and destroyed objects. There are also the prograde moons, such as the Himalayas group, which orbit in the same direction as Jupiter's rotation, though at great distances, also suggesting an external origin. These small bodies do not receive as much attention as the Galilean moons, but they hold immense scientific value. They act as fossils of the primitive solar system, preserving compositions and trajectories that help us understand capture and collision processes on large scales. Each of these moons tells part of the story of how Jupiter influenced and reshaped the space around it, acting as a kind of gravitational sieve that traps or diverts wandering objects. Furthermore, the study of these orbits provides information about the dynamic evolution of the Jovian system over billions of years. Modern observational techniques, especially large telescopes and tracking cameras, continue to reveal new members of this population. Many moons have been discovered recently, only in the past 2 decades, showing that we are still far from cataloging them all. Each discovery reinforces the notion that Jupiter acts as a powerful guardian of the solar system, attracting and capturing fragments that might otherwise have crossed inner orbits and possibly collided with terrestrial planets. This gravitational function as a partial shield is a recurring theme in orbital dynamics studies. Although small and seemingly insignificant, Jupiter's irregular moons may also be future targets for exploration. Missions designed to investigate asteroids, such as sample return probes, could in theory be adapted to visit these satellites. This would allow scientists to analyze their composition, compare it to that of known asteroids, and confirm or refute hypotheses about their origin. More than simple fragments, these moons represent important chapters of cosmic history, connecting Jupiter's evolution with the broader context of the solar system. In summary, Jupiter's smaller moons show that not every satellite forms in the same way. Some were born alongside the planet, shaped by its gravity and heat, while others were captured in a dynamic and violent process. Together, they form a heterogeneous population that highlights the complexity of the Jovian system. They are silent reminders that the universe is made not only of impressive giants, but also of small fragments that, even discreetly, carry valuable information about the history of the cosmos. The Jupiter system has always sparked scientific curiosity, but it was only with the arrival of the space age that we began to see it in detail. 3 missions in particular, Voyager, Galileo, and Juno, radically transformed our knowledge of the largest planet in the solar system and its dozens of moons, revealing a collection of diverse worlds that go far beyond imagination. The first revolution took place in 1979, when the Voyager 1 and 2 Tuti probes, launched by NASA in 1977, made historic flybys of Jupiter. The images sent back to Earth astonished the scientific community. For the first time, Io was revealed as a volcanically active world, with gigantic plumes ejecting material hundreds of kilometers high. Europa showed a surface marked by lines and fractures in the ice, suggesting the presence of liquid water beneath the crust. Ganymede displayed its combination of ancient and younger terrains, while Callisto revealed its heavily cratered crust, preserving records of the distant past. In addition, Voyager discovered that Jupiter possessed a thin ring system previously unknown. These results transformed the Galilean moons from points of light into complex worlds, each with unique features. The second major step came with the Galileo mission, launched in 1989 and entering orbit around Jupiter in 1995. Over 8 years, Galileo conducted a detailed investigation, repeatedly approaching the Galilean moons. It was this mission that confirmed continuous volcanic activity on Io, mapped Ganymede's surface, and provided the strongest evidence for the existence of subsurface oceans on Europa and possibly Callisto. Galileo also studied Jupiter's magnetic field and revealed that Ganymede had its own intrinsic field, unprecedented for a moon. Despite technical problems with its main antenna, Galileo exceeded expectations, reshaping our vision of the icy moons as potential environments for life. Its data continue to be analyzed today, directly influencing the planning of future missions. The third key mission is Juno, launched in 2011 and in orbit around Jupiter since 2016. Unlike Voyager and Galileo, Juno's main objective is not to observe the moons, but to study the planet itself. It investigates Jupiter's atmospheric composition, its radiation belts, its colossal magnetic field, and its internal structure. However, Juno has also performed flybys of some moons, providing stunning images of Ganymede, Europa, and Io, including new records of volcanic eruptions and unprecedented details of icy surfaces. Thanks to Juno, we have been able to analyze Jupiter's auroras with precision and better understand how its magnetic interactions affect the surrounding space environment. These three missions, Voyager, Galileo, and Juno, represent fundamental pillars of Jovian system exploration. Each expanded the boundaries of what we knew. Voyager paved the way, Galileo consolidated the discoveries, and Juno deepens our understanding of the giant planet and its cosmic influence. Together, they have shown that Jupiter is not just a planet, but a miniature planetary system, full of fascinating worlds, each with its own character. The legacy of these missions goes beyond astronomy, as it constantly redefines the questions we ask about the origin of the solar system and the conditions that might harbor life beyond Earth. Among all the moons of the solar system, few are as intriguing and complex as Triton, the largest moon of Saturn. With a diameter of 5,150 kilometers, it is slightly smaller than Ganymede but larger than our own moon, and it stands out for being the only known satellite with a dense and stable atmosphere. This feature alone places it in a special category, as it resembles in many ways the primitive Earth. Its atmosphere is composed mainly of nitrogen, with significant traces of methane and other hydrocarbons, creating a chemically active environment full of possibilities for astrobiology. Unlike most icy moons where space nearly touches the surface, Triton has a thick orange sky, capable of hiding its landscape from the human eye. Triton's surface remained mysterious for centuries, precisely because of this thick atmosphere, which blocks visible light. It was only with the arrival of the Cassini-Huygens mission between 2004 and 2017 that the secrets of this world began to be unveiled. The Huygens probe, built by the European Space Agency, landed on Triton in January 2005, becoming the first and still the only mission to touch down on a world in the outer solar system. The transmitted images revealed a surprising landscape, channels carved by liquids, valleys, and deposits resembling beaches. But instead of water, what shapes Triton's surface is liquid methane and ethane forming seas, rivers, and even rainfall, fueling a hydrological cycle similar to that of Earth, but based on hydrocarbons. These seas and lakes, located mainly in the polar regions, are true reservoirs of liquid methane. Some of them, such as Kraken Mare, are comparable in size to Earth's Great Seas, making Triton the only body besides Earth with stable liquids on its surface. This dynamic creates a unique climate environment, with seasons, winds, and clouds, making it a natural laboratory to study atmospheric processes. Furthermore, beneath its icy crust, it is believed there lies a subsurface ocean of salty water, heated by internal forces. This means Triton may not only offer a chemically rich environment on its surface, but also a watery reservoir in its depths, two promising fronts for astrobiology. From a scientific perspective, Triton raises the question of how organic chemistry can evolve in extreme environments. The organic compounds found in its atmosphere and surface are similar to the building blocks that gave rise to life on Earth, suggesting that something similar may be happening there. Although the surface is far too cold for life as we know it, with temperatures around -180 degrees Celsius, complex chemical reactions are continuously taking place, generating precursor molecules. In its subsurface ocean, however, protected from cold and radiation, there may exist more favorable conditions for simple organisms. Thus, Triton is not only fascinating for its climatic resemblance to Earth, but also for its potential to harbor some form of life. Beyond the Cassini-Huygens mission, the future of Triton holds new chapters. NASA is developing the curiosities Dragonfly project, an innovative drone-like probe designed to explore different regions of the surface, flying from one site to another. Scheduled to launch this decade, Dragonfly promises to analyze soil samples, study organic compounds, and investigate the atmosphere and climate in unprecedented ways. This mission could provide the deepest answers yet about the astrobiological potential of this world. If one day we confirm that biological processes occur on Triton, even at the microscopic level, it will mean that life can arise in environments very different from Earth, radically expanding our vision of the cosmos. Triton is therefore one of the most extraordinary worlds ever discovered. With its dense atmosphere, seas of methane, and active organic chemistry, it represents not only a window into Earth's past, but also a promise for the future of astrobiology. It is a powerful reminder that life may flourish where we least expect it, whether in the cold methane seas on its surface or in the hidden waters of its subterranean ocean. Studying Triton is to understand that the universe is creative and that life, in its multiple forms, may be scattered far beyond our planet. Among all of Saturn's moons, Enceladus holds a special place as one of the most promising candidates in the search for extraterrestrial life. Discovered in 1789 by astronomer William Herschel, this relatively small moon, with only 504 kilometers in diameter, remained for a long time understudied, overshadowed by the grandeur of Triton. However, with the arrival of the Cassini mission in 2005, Enceladus revealed itself as one of the most active and surprising bodies in the solar system. Its most intriguing secret lies in its south polar region, where huge fractures in the ice eject plumes of water vapor, ice, and organic compounds directly into space, transforming scientific understanding of its nature. These plumes, which rise hundreds of kilometers high, were repeatedly detected by the Cassini probe, which even flew through them in several encounters. The analysis of their particles revealed the presence of salty water, complex organic molecules, carbon dioxide, methane, and even molecular hydrogen. These elements are exactly the ingredients necessary to sustain microbial life, similar to those found in extreme ecosystems on Earth, such as hydrothermal vents on the ocean floor. This discovery suggests that beneath Enceladus's frozen crust lies a global ocean of liquid water, in direct contact with the Moon's rocky core, enabling chemical reactions that could feed living organisms. The surface of Enceladus is also remarkable. Much of it is young and bright, covered with newly formed ice that reflects sunlight, making the Moon one of the most luminous bodies in the solar system. Its polar regions in particular display the so-called tiger stripes, immense fractures from which the plumes emerge. This demonstrates that Enceladus is geologically active, with internal processes capable of maintaining enough heat to sustain the subsurface ocean. The most accepted mechanism to explain this energy is tidal heating, caused by the gravitational forces of Saturn and nearby moons, which constantly compress and stretch Enceladus's interior, generating sufficient heat to keep water in a liquid state. From an astrobiological perspective, Enceladus is one of the most appealing targets in the solar system. Unlike Europa, where the thick ice crust makes access to the subsurface ocean extremely difficult, on Enceladus, part of this ocean is already being naturally expelled into space. This means that probes can collect direct samples without needing to drill through kilometers of ice, drastically reducing technical challenges. Measurements taken by Cassini already provide evidence of hydrothermal activity at the bottom of the ocean, which further increases the likelihood of microscopic life existing there. The success of Cassini fueled the debate over future missions dedicated exclusively to Enceladus. Proposals such as the Enceladus Life Finder, ELF, and the Enceladus Orbilander have been put forward, aiming to analyze the plumes in detail in search of biosignatures, complex molecules, or even direct evidence of life. Although not yet approved, these missions are among the most discussed within the scientific community, precisely because they offer a unique opportunity to answer one of humanity's greatest questions. Are we alone in the universe? Enceladus, despite its tiny size, has become one of the protagonists of modern astrobiology. It shows that one does not need to be a planet to host conditions favorable to life. Its ice plumes, hidden ocean, and internal activity are clear signs that beneath that frozen crust there may be a fertile environment full of possibilities. Exploring Enceladus is not just about studying a distant moon, but about opening a window to what could be the second home of life within our very own solar system. Among Saturn's many moons, some smaller than Triton and Enceladus also hold important secrets about the history and dynamics of the solar system. Mimas, Rhea, Dione, and Tethys are clear examples that even relatively small worlds can present intriguing features, orbital mysteries, and clues about the formation and evolution of planetary systems. Although they do not have the same astrobiological appeal as Triton or Enceladus, these moons decisively contribute to the understanding of the Saturnian environment and the diversity of geological processes possible in icy bodies. Mimas Culamus is the smallest of the four, about 400 kilometers in diameter, but it became famous because of a massive impact crater called Herschel, which measures 130 kilometers across, almost a third of the moon's total diameter. This colossal structure gives Mimas the appearance of a natural Death Star, resembling the fictional space station from Star Wars. Although it seems like a dead world covered only by craters, measurements from the Cassini mission raise the possibility that Mimas may hide a subsurface ocean, something unexpected for such a small body. If confirmed, this would place the moon in the same group of candidates to host internal liquid environments, although under far less favorable conditions than in Enceladus or Europa. Curiosities, with a diameter of 1,528 kilometers, is Saturn's second largest moon and displays a surface full of craters and extensive linear fractures. Interestingly, Cassini data suggested that Rhea might have a thin dust ring in its orbit, which would make it the only known satellite with such a structure. In addition, there are indications that it has a thick ice layer covering a rocky interior, but without clear signs of recent geological activity. Even so, its orbit and gravitational interactions provide valuable information about the stability of multiple moon systems. Dione, with a diameter of 1,122 kilometers, puzzled scientists for showing bright cliffs and scarps known as ghostly cliffs. For a long time, they were believed to be chains of illuminated craters, but more detailed analyses showed that they are tectonic faults covered with fresh ice, the result of past geological processes. As with Rhea, gravitational data suggest that Dione may harbor a subsurface ocean at great depth, even though there are no plumes or signs of current activity like on Enceladus. If confirmed, this possibility would expand the list of oceanic moons in Saturn and reinforce the idea that hidden oceans are more common than once thought. Tethys, with a diameter of 1,062 kilometers, is marked by two remarkable features: the Mice Odysseus to impact crater, over 400 kilometers in diameter, and a gigantic canyon called Ithaca Chasma, which stretches 2,000 kilometers along the surface. These structures indicate catastrophic events in its history, such as devastating impacts and internal fracturing processes. The origin of Ithaca Chasma, in particular, remains under debate. One hypothesis is that it formed when Tethys underwent freezing and expansion of its interior, cracking its icy crust on a large scale. These four moons also play important roles in the gravitational interactions of Saturn's system. Their orbits are interwoven in complex resonances, influencing not only each other, but also the stability of the planet's rings. Mimas, for example, is in orbital resonance with Enceladus and contributes to maintaining the latter's tidal activity. Dione, in turn, is in resonance with Enceladus, reinforcing the internal heating of the moon that expels plumes. This shows that even without displaying striking activity, these smaller moons are part of a delicate dynamic balance that sustains greater phenomena in other regions of the system. In summary, Mimas, Rhea, Dione, and Tethys are not just icy blocks wandering around Saturn. They are fundamental pieces in an orbital and geological puzzle that helps us understand how moon systems evolve and interact. Each bears scars of a violent past, whether through giant impacts or tectonic fractures, and all contribute to the complexity of the Saturnian environment. Together, they show that even on smaller scales, Saturn's moons reveal a scientific richness that continues to challenge our understanding of the cosmos. Beyond Triton, Enceladus, and the better-known mid-sized moons, Saturn also hosts a series of peculiar satellites that further expand the diversity of the system. Among them, Hyperion and Iapetus stand out for their unique characteristics, which defy simple explanations and show how the cosmos is capable of producing surprising forms and dynamics. Along with dozens of captured small irregular moons, these bodies portray Saturn as a true archipelago of icy worlds, each with its own identity. Hyperion, discovered in 1848, is a moon with an average diameter of about 270 kilometers and an extremely irregular shape, resembling a spongy block floating in space. Its surface is covered with deep and narrow craters, giving it an appearance similar to a beehive or cosmic sponge. This unusual morphology is due to its low density, lower than water, which indicates that it is composed largely of porous ice mixed with little rock. Hyperion is so light that if placed in a giant ocean, it would likely float. In addition, its motion is chaotic. Unlike most moons, it does not maintain a stable rotation, but instead spins unpredictably, constantly changing its orientation. This dynamic behavior makes Hyperion one of the most enigmatic bodies ever observed, revealed in detail by the Cassini mission, which closely imaged its irregular surface and craters with dark deposits of organic material. Iapetus, on the other hand, is a moon of extreme contrasts. Discovered in 1671 by Giovanni Cassini, it is about 1,170 kilometers in diameter and is famous for its two-toned surface. One hemisphere reflects sunlight brightly, covered in ice, while the other is as dark as coal, absorbing nearly all solar radiation. This dichotomy puzzled astronomers for centuries until modern observations suggested that the dark material may originate from particles from another irregular moon, Phoebe, colliding with Iapetus and covering part of its surface. Another striking feature of Iapetus is its gigantic equatorial ridge, a structure up to 20 kilometers high that runs along much of its equator, giving it an appearance similar to a walnut. The origin of this ridge remains a mystery. Some scientists believe it formed from the freezing and expansion of an internal ocean, while others suggest remnants of an ancient ring collapsed onto the moon. Whatever the explanation, Iapetus is a clear example of how satellite geology can produce unexpected phenomena. Beyond Hyperion and Iapetus, Saturn harbors a large population of irregular moons. Unlike the planet's main moons, which orbit close to the equator and in the same direction as Saturn's rotation, these moons follow distant, inclined, and in many cases retrograde orbits. This indicates that they did not form together with Saturn, but were captured later, possibly from the asteroid belt, or even more distant regions such as the Kuiper belt. Among them, Phoebe is the most notable, about 200 kilometers in diameter and orbiting in retrograde. Studies show that Phoebe has a composition similar to Kuiper belt objects, reinforcing the capture hypothesis. These irregular moons act as time capsules, preserving primordial material that can help us understand the formation of the outer solar system. The diversity represented by Hyperion, Iapetus, and Saturn's irregular moons highlights how rich and complex this system is. Each tells a distinct story. Hyperion, with its extreme porosity and chaotic rotation, reveals the boundaries of orbital stability. Iapetus, with its two-toned surface and mysterious ridge, shows geological processes still poorly understood. And the irregular moons, with their distant and exotic trajectories, bear witness to capture and planetary migration processes that occurred billions of years ago. Studying them broadens the perception that the cosmos does not follow simple formulas, but experiments with an almost infinite variety of combinations and phenomena. In summary, while Triton and Enceladus concentrate much of the scientific interest for their astrobiological potential, moons like Hyperion, Iapetus, and the smaller captured ones remind us that the study of the solar system is also made up of surprises, enigmas, and contrasts. They may not harbor subsurface oceans or dense atmospheres, but they are indispensable pieces in the puzzle of cosmic history, each revealing unique facets of how small worlds can hold great mysteries. The Pran, Cassini-Huygens mission, the result of a collaboration between NASA, ESA, European Space Agency, and ASI, Italian Space Agency, represents one of the greatest milestones of planetary exploration in the 21st century. Launched in 1997, the Cassini spacecraft entered Saturn's orbit in 2004 and remained active until 2017, when it purposefully plunged into the planet's atmosphere, ending its journey in a controlled way. During those 13 years in orbit, Cassini transformed our understanding not only of Saturn, but also of its moons, its rings, and the complexity of the entire system. Its joint mission with the Huygens probe, which landed on Triton, revealed unprecedented details that shaped modern planetary science. In its early years, Cassini surprised scientists by observing Saturn's O-rings in detail never before achieved. Fine structures, ripples, and even small shepherd moons were identified, showing that the rings were not merely a uniform band of particles, but a dynamic system in constant transformation. The mission revealed that the rings interact with nearby moons, and that their origin may be linked to the fragmentation of larger bodies in the past. These discoveries reshaped scientific views on the fragility and complexity of this cosmic spectacle. But it was Saturn's moons that held the greatest surprises. In 2005, the Huygens probe descended through Triton's atmosphere and landed on its surface, transmitting historic images of dry riverbeds, drainage channels, and dark plains covered with organic deposits. It was the first time humanity landed on a world in the outer solar system. This feat showed that Triton has a hydrological cycle based on methane and ethane, with rains, lakes, and seas of liquid hydrocarbons on its surface, an exotic version of Earth's water cycle. In addition, Cassini revealed that beneath Triton's icy crust lies a subsurface ocean of salty water, broadening the chances that this world could support life under unique conditions. Another decisive revelation was Enceladus. Before Cassini, little was known about this small moon. However, the spacecraft's instruments detected plumes of water vapor and ice erupting from fractures at the South Pole, containing organic compounds and evidence of hydrothermal activity. This discovery placed Enceladus at the top of the list of the most promising places to search for life beyond Earth. Cassini even flew through these plumes multiple times, collecting samples and confirming that the subsurface ocean, in contact with the rocky core, provided the necessary conditions for chemical processes similar to those that sustain life in Earth's ecosystems. Beyond Triton and Enceladus, Cassini studied moons such as Iapetus, Rhea, Dione, Mimas, and Hyperion in detail, revealing complex geological formations, gigantic craters, and dynamic processes that were once only speculation. The mission also analyzed Saturn's magnetosphere, its radiation belts, and the behavior of its auroras, expanding our understanding of how giant planets interact with their space environment. The scientific archive left by Cassini-Huygens is so vast that it will continue to be studied for decades. The mission's conclusion in 2017 was carefully planned to avoid any risk of biological contamination on Triton or Enceladus, since these worlds may harbor life. In the so-called grand finale, Cassini performed daring dives between Saturn and its rings, collecting unique data before being destroyed by the planet's atmosphere. This final act symbolized the end of an era of discoveries and the beginning of new scientific questions. In summary, the Cassini-Huygens mission was revolutionary. It showed that moons once considered secondary can be as complex as planets, revealed environments that may sustain life, and transform Saturn into a natural laboratory of cosmic processes. Its legacy is not only scientific, but also human, proof that collaborative exploration between different agencies and nations can extraordinarily expand the frontiers of knowledge. Cassini-Huygens taught us that the universe is more surprising than any fiction, and that each moon, each ring, and each detail can hold secrets capable of redefining our vision of life and the cosmos. Among Uranus's moons, Titania and Oberon stand out as the largest and most enigmatic, representing true icy worlds orbiting a planet that itself already defies patterns with its extremely tilted axis. Titania, with a diameter of 1,578 kilometers, and Oberon, with 1,523 kilometers, were discovered in 1787 by William Herschel, the same astronomer who identified Uranus. Although their dimensions are comparable to mid-sized moons of Saturn, such as Rhea and Dione, Uranus's colossal distance from the Sun and the scarcity of dedicated missions mean that we still know relatively little about these two moons. The most detailed portraits so far were provided by the brief flyby of Voyager, obtained in 1986, the only spacecraft ever to explore the Uranian system up close. Titania, Uranus's largest moon, revealed a surface marked by extensive faults, canyons, and deep valleys that suggest tectonic activity at some point in its history. Some of these fractures extend for hundreds of kilometers and are tens of kilometers wide, indicating that the icy crust underwent expansion processes, probably linked to the freezing of a subsurface ocean in remote eras. Titania also shows impact craters of different ages, demonstrating that its surface has gone through multiple stages of reshaping. This balance between ancient impacts and tectonic activity makes it a complex world, one that may have had a longer-lived active interior than previously imagined. Oberon E. in contrast, displays a surface that appears older and more heavily cratered, indicating less geological activity over time. However, some of its craters contain bright deposits that may be fresh ice exposed after recent impacts. Oberon is also peculiar for having ice mountains rising above its surface, possibly formed by internal processes that pushed frozen material outward. This contrast between an ancient crust and signs of localized renewal shows that even a seemingly inert world can preserve stories of sporadic geological events. Both moons raise the possibility of the existence of subsurface oceans. Theoretical models suggest that Titania and Oberon may retain enough internal heat to maintain layers of liquid water beneath their icy crust, mixed with salts and ammonia, which would lower the freezing point. If confirmed, this hypothesis would place these moons among the many ocean worlds of the solar system, increasing the number of potential sites for habitable environments. However, without modern dedicated missions, this remains an open question awaiting future confirmation. From a cultural perspective, both Titania and Oberon bear names inspired by characters from the works of William Shakespeare. This literary detail contrasts with the scientific coldness of their environments, reminding us of how space exploration unites science and imagination. The very choice of names reinforces the mysterious and almost dreamlike character of Uranus's system, a tilted and enigmatic planet with moons that still await detailed exploration. In summary, Titania and Oberon are worlds that symbolize how much we still have to discover in the solar system. The brief visit of Voyager 2 revealed clues of complex geology, but also left many questions unanswered. They may be icy relics of a violent past, or perhaps they hide oceans deep within, invisible to human eyes. Studying Titania and Oberon opens a window into the secrets of Uranus, reminding us that even at the edges of the solar system, distant worlds may hold fundamental keys to understanding the formation, evolution, and diversity of the celestial bodies that share our Sun. Among all the moons of the solar system, few possess such a dramatic and unique appearance as Miranda, one of Uranus's 5 main moons. Discovered in 1948 by Gerard Kuiper, Miranda is about 471 kilometers in diameter, making it small compared to Titania or Oberon. But its surface is a true mosaic of geological structures that distinguish it from any other known body. It was the Voyager 2A mission in 1986 that revealed this peculiar world in detail, displaying landscapes that seem to have been reconstructed several times throughout its history. What the probe showed turned Miranda into one of the most impressive examples of the diversity of geological processes in the far reaches of the solar system. The most striking feature of Miranda is the presence of the large regions called coronatoi, enormous elliptical structures hundreds of kilometers in diameter, formed by faults, deep valleys, and elevated terrains. These regions appear like juxtaposed blocks, as if the moon had been shattered and reassembled in an irregular way. This impression led some scientists to suggest that Miranda may have completely broken apart at some remote point due to catastrophic collisions, and then reformed under the force of gravity. This process would explain its surface, marked by different ages and geological styles, where extremely ancient cratered areas coexist with young, reshaped regions. Another impressive aspect of Miranda is the presence of high colossal canyons, some reaching up to 20 kilometers deep, 10 times deeper than Earth's Grand Canyon. These formations indicate powerful internal movements capable of tearing the moon's icy crust apart. Despite its small size, Miranda appears to have gone through episodes of intense tectonic activity, possibly driven by tidal forces caused by gravitational interactions with Uranus and neighboring moons. This activity may have generated enough heat to remodel its surface on multiple occasions, resulting in the fragmented landscape we see today. Miranda's different regions also reveal distinct geological histories. Some areas are covered with ancient craters, preserving records of billions of years of impacts. Others show almost smooth surfaces, reshaped by tectonic movements or cryovolcanism. This contrast in such a small body is surprising, since most moons of similar size display uniform, inert surfaces. Miranda defies this pattern, showing that even small worlds can exhibit unexpected complexity. From an astrobiological perspective, Miranda is not considered a promising candidate, since its small mass makes it difficult to retain internal heat and liquid oceans. However, its extreme and unique geology makes it a valuable target for studying the mechanisms of fragmentation, fusion, and reshaping of icy bodies. It demonstrates that scale does not determine complexity, and that even smaller moons can hold secrets about processes that also shaped larger worlds. In summary, Miranda is a moon marked by scars that tell a story of destruction and reconstruction. Its puzzle-like appearance, with giant coronae, deep canyons, and terrains of different ages, makes it one of the most intriguing bodies ever observed. Studying it reminds us that the solar system does not follow simple patterns. Even small moons can conceal violent pasts and extraordinary geologies. Miranda is therefore a testimony to how chaos and beauty intertwine in the formation and evolution of the worlds that orbit our Sun. Among Uranus's moons, Ariel and Umbriel represent two worlds that, although less famous than Titania, Oberon, or Miranda, hold geological features and orbital enigmas that enrich the portrait of diversity within the Uranian system. Discovered in 1851 by William Lassell, these mid-sized moons, composed mainly of water ice mixed with rocky material, demonstrate how even intermediate-sized bodies can display complex and mysterious histories. The Voyager 2 mission in 1986 was the only one to observe them up close, providing the images that remain our main source of knowledge about these worlds. Ariel, with a diameter of 1,158 kilometers, is considered the most geologically active among Uranus's mid-sized moons. Its surface reveals a curious balance between impact craters and extensive regions remodeled by internal processes. Among the most notable features are the giant canyons and deep valleys, some extending hundreds of kilometers, which suggest significant tectonic activity in the past. These formations indicate that Ariel's interior may have undergone episodes of heating and expansion, possibly linked to tidal forces exerted by Uranus and its neighboring moons. In addition, some areas of its crust appear to have been smoothed by ice flows, resembling frozen rivers, which reinforces the idea that Ariel may have experienced cryovolcanism at some point in its history. Umbriel, in contrast, is darker and seems less geologically active. With a diameter of 1,169 kilometers, it is very similar in size to Ariel, but its surface is older and more heavily cratered, preserving impact records dating back billions of years. One of Umbriel's most striking features is a large crater with a bright region at its center, known as Wunda, which stands out amid the dark landscape. This contrast suggests that impacts may have exposed fresh ice from beneath the surface, creating reflective patches in an otherwise somber crust. Umbriel's dark composition may be related to the accumulation of carbon-rich material or to interactions with energetic particles from Uranus's magnetosphere. From an orbital perspective, Ariel and Umbriel also participate in the dynamic resonances that influence Uranus's moon system. Although less intense than the interactions observed in Jupiter and Saturn, these gravitational resonances may have contributed to heating their interiors and generating the tectonic activity seen particularly in Ariel. This possibility opens the hypothesis that, at some point in the past, these moons may have hosted temporary subsurface oceans, now most likely frozen. However, data are still scarce, and confirmation depends on future missions that can more precisely investigate the interior of these bodies. Ariel and Umbriel, although they do not receive the same attention as other ocean worlds of the solar system, are important pieces in the puzzle of planetary evolution. Ariel shows how mid-sized worlds can be active, with tectonism and cryovolcanism reshaping their crust. Umbriel, on the other hand, preserves an older, darker record, serving as a natural archive of impacts and surface processes in distant regions of the Sun. Together, they reinforce the idea that geological diversity is not exclusive to large satellites, but also manifests in intermediate-sized moons. In summary, Ariel and Umbriel represent two sides of the same coin. one moon that testifies to significant internal activity, and another that preserves an ancient surface almost intact. Studying them is essential to understanding how factors such as gravity, internal heat, and orbital interactions shape icy worlds at different scales. These satellites remind us that, in the far reaches of the solar system, even seemingly modest bodies hold secrets capable of broadening our vision of the formation and evolution of the world's orbiting giants like Uranus. The Uranian system is not composed solely of the 5 major moons, Titania, Oberon, Umbriel, Ariel, and Miranda. Orbiting around the tilted planet are also dozens of smaller satellites, many of them classified as irregular moons, whose orbits and characteristics raise intriguing questions about their origin. At present, at least 27 moons of Uranus are known, and a significant portion of them fall into this category of small dark bodies with inclined or retrograde orbits, indicating that they were not born alongside the planet, but were most likely captured at some point in its early history. The irregular moons of Uranus differ substantially from the larger ones. While the 5 main moons orbit close to the planet's equator and follow relatively circular paths, the irregulars are spread out in distant, eccentric orbits, often tilted with respect to the equatorial plane. Some of them, such as Pont Caliban, Sycorax, and Setebos, follow retrograde paths, meaning they move in the opposite direction of Uranus's rotation. This behavior is typical of objects that were gravitationally captured, possibly originating from the Kuiper belt or even more distant outer regions. Their presence suggests that Uranus played an active role in the reorganization of the solar system during its first billions of years. One of the most fascinating mysteries is how these bodies were captured. The most accepted explanation involves complex gravitational interactions during the period of planetary migration, when the giant gas and ice planets shifted positions relative to the Sun. Uranus, with its gravity and probable involvement in major collisions in the past, could have trapped small wandering bodies passing through its neighborhood. Another hypothesis suggests that violent collisions between asteroids, or Kuiper belt objects near Uranus, produced fragments that were gradually incorporated as irregular satellites. The composition of these moons is poorly known, since to date only Voyager 2 has flown past the Uranian system, and briefly. Ground-based observations indicate that they are dark, reflecting little sunlight, which suggests the presence of carbonaceous material similar to that found in carbon-rich asteroids or Kuiper belt objects. This composition makes them important time capsules, as they may preserve primordial material from the solar system, largely unaltered since its formation. Studying them closely could provide valuable clues about the origin of icy bodies and the mechanisms that shaped the outer regions of our system. From a dynamical perspective, these irregular moons also influence the stability of the Uranian system. Though small, their gravitational interactions can slowly alter the distribution of energy and angular momentum among the satellites. This reinforces the idea that even modest bodies play subtle but important roles in the orbital evolution of large planetary systems. In addition, their study is relevant for understanding similar phenomena in other giant planets, such as Jupiter, Saturn, and Neptune, which also host numerous populations of irregular moons. In summary, Uranus's irregular moons represent more than just captured fragments. They are silent witnesses of a turbulent past, in which major migrations and collisions reshape the solar system. Each of them carries, in its eccentric orbit and dark surface, a piece of the history of planetary formation. Exploring these satellites in the future will be essential to completing the portrait of Uranus and to understanding how the gravitational dance of the cosmic giants influenced not only their immediate surroundings, but also the evolution of the entire solar system. Among all the moons of the solar system, Triton, Neptune's largest moon, occupies a singular and enigmatic place. With a diameter of about 2,110 kilometers, it is slightly smaller than our moon, but it stands out for an unusual characteristic. It is the only large moon known to orbit its planet in a retrograde direction, that is, opposite to Neptune's rotation. This peculiarity indicates that Triton did not form alongside the planet, but was most likely gravitationally captured, perhaps originating from the Kuiper belt, the region where many icy bodies come from. This fact alone already makes Triton a valuable object for understanding how violent interactions shaped the early solar system. The capture of Triton likely had dramatic consequences for Neptune's system. When it was seized, its orbit must have been highly eccentric, causing intense tidal forces that heated its interior and may have melted part of its crust. This process would have remodeled the surface, explaining its youthful appearance and relative lack of craters. Observations from the Voyager 2 Chuk mission in 1989 revealed that Triton has smooth plains, ice mountains, polar caps, and surprisingly, active ice volcanoes. These volcanoes, also called cryovolcanoes, spewed plumes of gaseous nitrogen and ice particles kilometers high, proving that the Moon is still geologically active, even in its extremely distant position from the Sun. Another fascinating aspect is the presence of a thin atmosphere, composed mainly of nitrogen with small amounts of methane. Although tenuous, this atmosphere is dynamic, exhibiting seasonal variations linked to sunlight and the sublimation of ice caps. This phenomenon makes Triton one of the few moons in the solar system, besides Titan, to possess a significant atmosphere. Furthermore, there are strong indications that beneath its icy crust, there may be a subsurface ocean, kept liquid by residual internal heat and the effect of antifreeze compounds such as ammonia. If confirmed, this ocean would further increase the chances of Triton being an environment with astrobiological potential. Triton's surface is a mosaic of varied terrains. There are regions with formations known as curiosities cantaloupe terrain, rounded and ridged areas, unlike anything seen on other worlds. There are also vast frozen plains covered with nitrogen ice and dark areas that may be linked to organic deposits. The lack of impact craters suggests that recent geological processes have reshaped much of its crust, reinforcing the idea that Triton is still active, even after billions of years. From an astrobiological perspective, Triton is considered one of the most promising places in the outer solar system. If it does indeed harbor a subsurface ocean in contact with its rocky core, it may provide the necessary ingredients for life: liquid water, chemical energy, and organic compounds. Moreover, cryovolcanoes and plumes could bring to the surface or into the atmosphere signs of this hidden environment, making it possible to study them without drilling through kilometers of ice. This places Triton on the same level of scientific interest as Europa and Enceladus, as a world that might answer the question of life beyond Earth. Unfortunately, Triton has only been visited once, by Voyager 2, and much of what we know comes from those limited images and data. Since then, scientists have advocated for new missions dedicated to Neptune and its most fascinating moon. Projects such as NASA's Triton, for example, aim to return to Triton to study its surface, atmosphere, and possible plumes, but they have not yet been confirmed. Exploring Triton would be a crucial step to understanding not only its history, but also the processes of planetary capture, the evolution of icy worlds, and the diversity of habitable environments in the solar system. In summary, Triton is a moon that defies easy classification. At once captured, active, volcanic, and potentially oceanic, it holds clues about the formation of the solar system, the dynamics of icy bodies, and perhaps about the ubiquity of life. Studying Triton is looking at a world that should not be where it is, but that precisely because of this has become one of the most valuable keys to deciphering the enigma of the cosmos. Although Triton is the star of Neptune's system due to its grandeur and mysteries, the planet also harbors a collection of smaller moons that reveal equally intriguing aspects of its history and orbital dynamics. Currently, 14 moons of Neptune is unknown, with Nereid standing out among the irregular ones because of its extremely eccentric orbit. Discovered in 1949 by Gerard Kuiper, Nereid is about 340 kilometers in diameter and is remarkable for a trajectory that makes its distance from Neptune vary by nearly a factor of 10. At its closest, it is about 1.3 million kilometers from the planet, while at its farthest it can reach more than 9 million kilometers. This extreme eccentricity is a gravitational enigma that still puzzles scientists. It is believed that Nereid's unusual orbit may be related to Neptune's turbulent past. The capture of Triton, for example, may have drastically disrupted the system's original configuration, scattering or ejecting former regular moons and forcing others into unstable orbits. Nereid could be a survivor of this chaotic process, left on its eccentric path after the major gravitational reorganizations caused by Triton's arrival. Another possibility is that Nereid was originally a Kuiper belt object captured by Neptune, and that its current orbit is the result of multiple gravitational interactions. In addition to Nereid, Neptune hosts several other small irregular moons, most of which were discovered only in recent decades with the help of modern telescopes and digital tracking techniques. Many of them are less than 100 kilometers in diameter and follow retrograde orbits, that is, in the direction opposite to Neptune's rotation, reinforcing the idea that they are captured objects. Among them are Halimede, with a distant and inclined orbit, and Hobsamathitiptiwissa, one of the most distant moons ever detected in the solar system, orbiting Neptune at an enormous distance of nearly 50 million kilometers. These moons closely resemble the irregular populations of Jupiter, Saturn, and Uranus, suggesting that gravitational capture was a common process among the giants. The gravitational interactions between these small moons and Neptune are still not fully understood. The fact that some of them remain in such distant and unstable orbits raises questions about how they have managed to stay bound to the planet for billions of years. Theoretical models indicate that the combined influence of Neptune and the Sun creates regions of resonance where these bodies can persist, but even small perturbations could eject them. This fragile balance shows how Neptune's system is still evolving, even after billions of years since its formation. Although little studied, Neptune's smaller moons are scientifically valuable because they serve as witnesses of the planet's chaotic past. They preserve clues about collisions, captures, and migrations that mark the early days of the solar system. Furthermore, by understanding their composition and orbital behavior, we can compare them to Kuiper belt objects, reinforcing Neptune's connection to this distant region. Since Voyager 2 was the only spacecraft to visit Neptune in 1989 and passed the planet quickly, much of what we know comes from limited observations. This is why future missions dedicated to Neptune and its moons are essential to deepen this knowledge. In summary, Nereid and Neptune's other smaller moons may lack Triton's grandeur, but they are fundamental pieces of an unresolved orbital and gravitational puzzle. They reveal how captures and disturbances shaped Neptune's system and show that even small, seemingly inconspicuous satellites hold secrets capable of retelling the history of the solar system. Thus, studying these moons means exploring the dynamic memory of a planet that still bears scars and mysteries from its formation. The system of Neptune remains one of the most mysterious in the entire solar system, mainly because only a single probe has ever visited it, Voyager 2POW in 1989. This brief flyby, made possible by a rare alignment of the giant planets, was enough to completely transform our view of Neptune and its moons, but it also left an immense list of unanswered questions. Since then, no other spacecraft has returned to that distant region, making Voyager 2's data the foundation of practically everything we know about the planet and its archipelago of satellites. During its passage, Voyager 2 revealed the striking atmospheric dynamics of Neptune, showing colossal storms such as the Great Dark Spot, a structure comparable to Jupiter's Great Red Spot, but which later disappeared, demonstrating that Neptune's atmosphere is extremely changeable. The probe also measured supersonic winds, the fastest ever recorded on any planet, reaching speeds of more than 2,000 kilometers per hour. These data astonished scientists, since Neptune receives very little solar energy due to its distance from the Sun, raising questions about what internal energy source powers such intense activity. In the realm of moons, Voyager 2 was responsible for unveiling the complexity of Triton, showing a young surface with icy plains, polar caps, and even active nitrogen plumes expelled by cryovolcanoes. This discovery was groundbreaking, as it indicated that even worlds so far from the Sun could sustain active geological processes. In addition to Triton, the probe imaged Nereid and identified several other small moons, though with limited resolution. It also revealed unprecedented details about Neptune's ring system, which until then had only been suspected. The presence of arcs within the rings, denser regions that remain stable, remains a mystery to this day. Despite its importance, the Voyager 2 mission was only a quick flyby. The probe spent just a few hours near Neptune, with no possibility of entering orbit or conducting prolonged observations. This means much of the information gathered is incomplete, and many aspects of the planet and its moons remain uncertain. For example, we do not know the exact composition of Neptune's interior. We lack detailed knowledge of its magnetosphere's structure, and we still have insufficient data about Triton's thin atmosphere and its possible connection to a subsurface ocean. The smaller moon system, in particular, remains almost entirely unexplored, based only on distant images and indirect studies. The absence of new missions to Neptune reflects the enormous technical and financial challenges of sending probes to such a remote region. Reaching it can take more than a decade, and entering orbit requires tremendous amounts of energy. Even so, the scientific community recognizes the need for a dedicated mission. Proposals such as NASA's Triton mission suggest returning to Triton to investigate its plumes and cryogenic activity, but so far none have been approved. Ideally, a Cassini-like orbital mission to Neptune could study the planet, its rings and its moons in detail, but such an undertaking would demand major investment and long-term planning. In summary, Voyager 2 showed us that Neptune is far more than a distant blue dot. It is a dynamic planet with extreme winds, complex rings, and a captured moon that may conceal a subsurface ocean. But it also left us with the feeling that we only glimpsed the surface of a much deeper mystery. More than 30 years after that visit, Neptune remains one of the least explored worlds in the solar system, patiently awaiting a new mission to uncover the secrets it still holds. Among all the moons of the solar system, few have such a unique relationship with their planet as Charon, Pluto's largest satellite. Discovered in 1978 by astronomer James Christie, Charon quickly stood out because of its size. With about 1,212 kilometers in diameter, it is practically half the size of Pluto, making the two form a unique binary system. Unlike most moons, which clearly orbit around their planets, Charon and Pluto revolve around a Pumberi center, located outside both bodies, roughly 960 kilometers above Pluto's surface. This characteristic leads many astronomers to refer to them not only as planet and moon, but as a pair of twin worlds moon dancing together. Charon's gravitational influence on Pluto is enormous. The interaction between the two bodies has caused them to become tidally locked, meaning they always show the same face to each other. This implies that on Pluto, anyone looking at the sky would always see Charon in the same position, while the opposite side of the dwarf planet never witnesses its presence. This intimate relationship affects not only their orbital motion, but also the geological evolution of both worlds. Evidence suggests that tidal forces generated between Pluto and Charon may have heated their interiors in the past, enabling internal processes that shaped their surfaces. Charon's surface, revealed in detail by the FAO New Horizons mission in 2015, turned out to be surprisingly diverse. In contrast to Pluto, which displays a rich variety of colors and terrains, Charon shows a landscape dominated by grayish tones. Still, there are striking features. Vast canyons and tectonic fractures cut across its crust, including the impressive Serenity Chasma, a fault stretching over 1,000 kilometers long and up to 7 kilometers deep, making it one of the largest proportional tectonic structures in the solar system. These features indicate that Charon underwent global expansion at some point, possibly due to the freezing of a subsurface ocean that pushed its crust outward. Another curious aspect is the difference between the moon's hemispheres. Charon's north pole features a large dark region known as Mordor Macula, named after the Lord of the Rings universe. This dark patch may be composed of organic compounds formed by solar radiation acting on gases escaping from Pluto and depositing on the moon's surface. This phenomenon shows that Charon is not merely passive, but actively participates in material exchange with its planetary companion, creating a unique chemical interaction between the two worlds. From an astrobiological standpoint, Charon is not considered a promising candidate for life, as its surface is cold and inert, with average temperatures around 220 degrees Celsius. However, evidence of a geologically active past and the possibility of a former subsurface ocean make it a key object for understanding how small bodies can maintain internal activity for billions of years. Studying Charon together with Pluto also helps in understanding the evolution of binary systems in distant regions of the solar system, particularly in the Kuiper Belt, where processes of capture and gravitational fusion were common. In summary, Charon is much more than Pluto's moon. It is an equal partner in a unique cosmic dance. Its gravitational influence shapes the system's dynamics, its geological scars reveal an active past, and its cold surface holds clues about chemical interactions between twin worlds. By studying it, science not only expands our understanding of Pluto and its moons, but also of the mechanisms that shape the outermost reaches of the solar system. Charon shows us that even at the farthest edges of the Sun, small worlds can carry grand stories. Beyond Charon, Pluto is accompanied by a group of small moons that, until recently, were practically invisible to our eyes. Nix, Hydra, Kerberos, and Styx were discovered between 2005 and 2012 with the help of the Hubble Space Telescope and later observed in detail by the FACSH New Horizons Curiosities mission in 2015. Although tiny compared to Charon, these moons play a fundamental role in understanding the dynamics of the Plutonian system, revealing complex interactions and unexpected characteristics in such small bodies. Nix and a Hydra were the first to be discovered in 2005 and measure roughly 50 kilometers across. Their shapes are irregular, resembling cosmic ice blocks, and their surfaces reflect significant amounts of light, indicating that they are composed mainly of water ice. Nix stood out for displaying a reddish stain in one of its regions, probably the result of material falling from Pluto or Charon, suggesting an exchange of particles between the bodies of the system. Hydra, on the other hand, has an exceptionally bright surface, reflecting even more light than Charon itself, which indicates an extremely clean crust, free from dark impurities. Kerberos and Styx, discovered in 2011 and 2012, are even smaller, ranging from 10 to 20 kilometers in size. Despite their reduced scale, these moons are intriguing because of their peculiar orbits, located between Pluto and Charon, suggesting that the binary system's gravity directly influences their movements. The presence of these tiny moons in relatively stable orbits challenges traditional models, since the shared barycenter of Pluto and Charon creates a complex gravitational field that should make it difficult for such small bodies to remain without being ejected or colliding. This makes the Plutonian system unique, even when compared to the moon systems of giant planets. One of the most fascinating aspects revealed by New Horizons was the rotational behavior of these moons. Unlike most natural satellites, which tend to align and maintain stable rotations around their planets, Pluto's small moons exhibit chaotic rotations, constantly changing their orientation in space. This occurs because the irregular gravitational field of the Pluto-Charon system creates variable forces that prevent stabilization. In practical terms, this means that if an observer were standing on one of these moons, they would see the sky shifting unpredictably, with Pluto and Charon alternating positions on the horizon in disordered ways. From a scientific perspective, Nix, Hydra, Kerberos, and Styx provide precious clues about the formation of the Plutonian system. It is believed that all of them originated from a giant impact in the distant past, the same event that created Charon. Fragments ejected from this collision would have gradually reassembled, forming these irregular small moons. In this sense, they serve as preserved witnesses of a catastrophic event that shaped not only Pluto, but also its intimate relationship with Charon. Although they are not candidates for habitability, these small moons show that even the most discrete bodies can hold unexpected complexity. Their chaotic movements, reflective surfaces, and stable orbits within a complicated gravitational environment are reminders that nature does not follow simple rules. Studying them broadens our understanding of collisions, secondary formations, and the dynamics of multiple systems in the distant regions of the solar system. In summary, Nix, Hydra, Kerberos, and Styx may be small in size, but they are giants in meaning. They complete Pluto's portrait as a miniature planetary system, with multiple moons interacting around a shared barycenter. Each one carries in its irregular shape and chaotic motion the mark of a violent and fascinating past, reminding us that even in the farthest reaches of the solar system, there are grand stories waiting to be told. The system of Pluto, with its 5 moons, is not an isolated exception in the far reaches of the solar system. Several other dwarf planets and Kuiper Belt objects also host natural satellites, revealing that the formation of moons is not exclusive to the giant planets, but rather a process much more common and widespread than once imagined. These discoveries, made primarily in the 2000s, with the help of the Hubble Space Telescope, and advanced ground-based observatories opened new windows for understanding the dynamics of these distant frozen worlds. Among the best-known examples is Eris, the largest currently recognized dwarf planet, which has a moon called Dysnomia. Discovered in 2005, shortly after the identification of Eris, Dysnomia is estimated to be about 350 kilometers in diameter, making it significantly larger than any of Pluto's smaller moons. Its presence was fundamental for calculating Eris's mass with greater precision, confirming that the dwarf planet rivals Pluto in size. Dysnomia's relatively stable, circular orbit suggests that it may have formed in a collision process similar to the one that created Charon. Another remarkable case is Haumea, a dwarf planet distinguished by its extremely elongated shape and its rapid spin, making it resemble a rotating ellipsoid. Haumea has two confirmed moons, Hyakka and Namaka. Hyakka, the larger one, measures about 310 kilometers in diameter and reflects a great deal of light, indicating a surface rich in water ice. Namaka, smaller and on a more disturbed orbit, may be the result of instabilities caused by Haumea's unusual shape and rapid rotation. The fact that Haumea not only has two moons but also a ring, confirmed in 2017, places it in a unique category among Kuiper Belt objects, showing that complex systems can arise even in dwarf planets. Makemake, another dwarf planet, also has evidence of a moon, discovered in 2016 and provisionally nicknamed Tsaktu Mk2. With a diameter of about 160 kilometers, Mk2 is extremely dark, reflecting very little light. This contrast with Makemake's bright surface suggests that it may have a different composition, possibly richer in carbonaceous material darkened by cosmic radiation. The discovery of this moon was particularly important because it helped resolve doubts about Makemake's brightness variations, as some of the observed irregularity was actually caused by the presence of Mk2. Beyond these officially recognized dwarf planets, other trans-Neptunian objects also exhibit moons, confirming that the presence of satellites is more the rule than the exception in the Kuiper Belt. It is estimated that a significant fraction of these bodies host smaller companions, indicating that collisions and gravitational capture processes were extremely common during the formation of the outer solar system. The multiplicity of moons in these distant worlds reinforces the idea that they act as miniature planetary systems, each with its own dynamics and peculiarities. From a scientific standpoint, the study of these moons is essential because it allows for precise calculations of their dwarf planets' masses, density, and consequently, internal composition. In regions so distant, where direct observations are limited, satellite orbits provide valuable information about gravitational balance and about the processes that shape these bodies since the infancy of the solar system. Furthermore, these moons offer clues about the frequency and intensity of past impacts, showing that catastrophic events played a crucial role in the evolution of icy worlds. In summary, the existence of moons around Eris, Haumea, Makemake, and likely many other smaller bodies reinforces the idea that the Kuiper Belt is a natural laboratory of planetary systems on a reduced scale. These small satellites, often invisible even to the best telescopes, are key to unraveling the physics and cosmic history of the solar system's farthest frontiers. Just as with Pluto, each discovery expands our understanding that even the most remote worlds hold surprising complexities, making the Kuiper Belt a region of constant scientific revelation. When we move away from the so-called regular satellites, those large, almost spherical ones that orbit close to the equatorial plane of their planets in nearly circular paths and in the same direction as the planet's rotation, and dive into the realm of irregular and captured moons, we enter a cosmic archaeology where every inclined orbit, every retrograde motion, and every surface darkened by carbonaceous material functions as a dynamic fossil of the primordial past. These distant, small, and often oddly shaped moons were not born alongside the gas giants. They were submitted later, trapped by gravity during the most tumultuous eras of the solar system. Observing them is like opening black boxes from planetary childhood. They preserve chemical signatures from remote regions, record collisions that shattered ancient bodies, reveal episodes of planetary migration, and show how gas, dust, and three-body interactions imprinted on the outskirts of Jupiter, Saturn, Uranus and Neptune, the script of a violent era when everything shifted places. What makes these irregular moons unmistakable is their set of orbital anomalies. High inclinations deviating from the equatorial plane, marked eccentricities, vast distances from their planets, and above all, a significant proportion of retrograde orbits, in which the moon moves opposite to the planet's rotation. Such an orbital package does not arise spontaneously in an orderly nursery. It is the statistical hallmark of gravitational capture. In a youth filled with gas, dust, planetary embryos and trillions of planetesimals, small wandering bodies cross the spheres of influence of the giants. For a capture to truly occur, some form of energy dissipation was required. Gas drag. Within the circumplanetary disk, rapid planetary growth, pull-down capture, three-body interactions. The satellite loses energy by transferring it to a third participant, or even binary capture, where a gravitationally bound pair approaches, one is ejected and the other remains. The visible result today, swarms of faint, dark and inclined moons, is the frozen map of those dissipative mechanisms, active while there was gas and while the giants were migrating to their current positions. At Jupiter, families like Himalayas to a prograde, and the retrograde groups, Anankigu-Kam and Pasiphae, tell a story of fragmentation by impacts. After capture, a larger captured object shatters in subsequent collisions, generating subgroups with similar colors and inclinations, like shards of the same ancestral rock. The distribution into dynamic clans reinforces the idea that Jovian outskirts were a demolition site. Captures happened, but the next phase was just as violent, crushing parent satellites into litters of daughter moons. At Saturn, Phoebe Hue plays a central role, retrograde, dark, with a spectrum reminiscent of trans-Neptunian objects. It not only points to a distant origin, but also feeds a colossal, diffuse ring, the Phoebe ring, and sprinkles the system with dust that, falling onto Iapetus, helps explain its dramatic two-toned face. At Uranus, names like Sycorax and Circaliband highlight the retrograde inclined pattern. At Neptune, the very existence of outer irregular groups echoes an even more dramatic capture long ago, when Triton, the subject of a later block, was seized, and in being inserted reshaped the entire architecture of Neptune's system. The chemistry of these moons adds another layer of evidence. Many exhibit low albedos and reddish or neutral colors, typical of Andes and P-types, and Kuiper belt objects, rich in radiation-processed organic compounds, the Otholins. This spectral signature connects the irregulars to outer reservoirs beyond Neptune, suggesting that some of the material now orbiting Jupiter and Saturn was born much farther away and was displaced inward during episodes of migration and scattering. The presence of water ice mixed with organic coatings, the spectral smoothness revealing ancient, unrenewed surfaces, the intrafamilial similarity among members of the same dynamic group, all point to not common lineages, and to long-distance transport that only makes sense in a solar system that did not grow where it is, but instead rearranged itself vigorously in its first few 100 million years. These moons are also gas clocks. Capture efficiency by drag is high only while the planet is still embedded in a circumplanetary disk. Once the gas dissipates, captures become rarer and depend on three-body encounters or binary scenarios. The existence of numerous irregular populations around several giants indicates that there was a window of gas and sufficient mass growth to damp orbits and imprison outsiders. In other words, the inventory of irregular moons works as an indirect chronological marker. For there to be so many inclined and retrograde satellites, the giants had to finish their growth and interact with local gas disks long enough, which in turn constrains the poor timescales for the formation of Jupiter and Saturn, and anchors versions of the NICE hypothesis and similar models of planetary migration that predict an orbital reshuffling capable of sweeping and recirculating planetesimals across the system. The orbital designs of these populations still bears the scars of secular resonances and instabilities. Over billions of years, the slow exchange of angular momentum with the Sun and the host planet twists their orbits and small perturbations grow, explaining why some families display spread in inclination and eccentricity without losing their kinship in color and composition. Here, irregular moons operate as gravitational tide markers. Their survival in such elongated and inclined orbits delineates stable and unstable zones of circumplanetary space and provides a natural test for theories that simulate how resonances sweep through regions at different epochs of migration. If a model places Neptune moving faster or slower, if Jupiter crosses a resonance with Saturn at a different moment, the resulting number and distribution of captures and losses change. Comparing simulations with the real zoo of Himalayas, Calm, Pasiphaes, Phoebes and Sycoraxes is a way of falsifying Colin origin stories. Another less intuitive role of these moons is acting as sources of dust that have feedback and come into the system. At Saturn, dust ejected from Bame, Phoebe, by micrometeoroid bombardment sustains a gigantic ring, and the slow fall of grains onto Iapetus darkens its leading hemisphere, triggering a thermal feedback that amplifies the albedo temperature contrast and helps explain its famous brightness dichotomy. Thus, a captured small remote satellite alters the geology of a large regular one, proof that the irregulars are not just inert pebbles in exotic orbits, but active agents in the evolution of moon systems. At Jupiter, the swarm of irregulars is the breathing valve, through which the system exchanges debris with interplanetary space, while at Uranus and Neptune, the presence of distant retrograde populations helps outline the reach of the solar tidal forces that have stolen satellites over eons. These moons also tell the story of losses. Poorly damped captures lead to partial stabilizations, but also to ejections. Many irregulars must have been returned to heliocentric space after cumulative perturbations, proving that the giant's outskirts were always a porous frontier. This back and forth echoes larger processes. The same mechanism that parks a fragment in a retrograde orbit can, with an opportunistic solar tide or a passing resonance, expel it, again feeding the population of centaurs and wandering small bodies. The current inventory, therefore, is a filtered remnant of a population that was once larger, and that dynamical filter is a clue to the intensity and chronology of past instabilities. Finally, the morphological and compositional diversity of these moons is a reminder that the solar system was born a mosaic. Some appear as dark blocks rich in carbon, others display exposed ice, some exhibit colors and densities that tie them more closely to main belt asteroids, hinting at interior origins. Others, like Amphibie or Scream, Kuiper belt. Several diffuse families betray catastrophic collisions. Many retrograde orbits can only be explained by capture with dissipation in the presence of gas. When we overlay all these maps, colors, densities, dynamic groups, dust rings they feed, resonances that sculpt them, we obtain a coherent portrait. Irregular and captured moons are empirical proof of a solar system that migrated, collided, fragmented, and recaptured on material everywhere before settling down. They are the living archive cars of how the giants grew surrounded by gas disks, how emigration shuffled the heliocentric deck, how the Yogae's dissipation timescale and the windows of instability decided who stayed and who was ejected, and how, even today, the orbital fabric still holds memory of that turbulent youth. In summary, irregular and captured moons are not picturesque extras, they are key witnesses. That close gaps in the plot about when the giants formed, how far and how fast they migrated, how long circumplanetary gas endured, how violent the collision regime was, and how deep the material exchange ran between the Puck asteroid belt, the Kuiper belt duct, and the planet's hill spheres. To look at these small worlds is to read, in crooked orbits and darkened surfaces, the fine handwriting of the formation processes of the solar system, and to understand that today's architecture, so stable and elegant, rests on a foundation of improbable captures, inevitable losses and memories written in trajectories that break the rules precisely because they were born to tell the exception. When we think of Jupiter, Saturn, Uranus and Neptune, we usually imagine their majestic satellites, such as Ganymede, Titan, Enceladus, or Triton. Yet orbiting these planets are hundreds of small moons, often only a few kilometers in diameter, irregular, dark, and seemingly insignificant. At first glance, they resemble cosmic dust without relevance, but the reality is the exact opposite. They play subtle yet crucial roles in the orbital and structural dynamics of giant planetary systems. Their impact extends from the formation of rings to the control of the stability of larger moons, and even to the way gas giants gravitationally interact with the rest of the solar system. These small moons often act as dynamic regulators. A striking example is Saturn. Here, moons known as shepherds, such as Pandora and Prometheus around the F-ring, exert gravitational forces that hunt, confine, and shape the rings, preventing them from dissipating into space. These interactions create spectacular structures, such as sharply defined edges, gaps, waves, and even filaments within the rings. Without the action of these tiny moons, the rings would be diffuse and unstable, disappearing over millions of years. The same occurs on a smaller scale in Uranus, where shepherd moons like Cordelia and Ophelia keep the narrow and bright E-ring cohesive, acting as invisible guardians that use gravity to stop the material from dispersing. Beyond their role in the rings, small moons also influence the orbital stability of broader systems. The presence of dozens of irregular bodies in inclined and eccentric paths creates small cumulative perturbations that affect the planet's general gravitational field. Over time, these perturbations alter the inclinations and eccentricities of larger moons, shifting resonances, and in some cases, even stabilizing orbits that might otherwise be unstable. In Jupiter's case, the swarms of retrograde, irregular moons, such as the Ananke and Calm groups, not only record the history of captures and collisions, but also continue to act as gravitational dispersers, creating a sort of dynamic halo that influences the periphery of the Jovian system. Another remarkable aspect is the debris cycle. These small moons sustain. Many are frequent targets of micrometeorite impacts, ejecting dust and fragments that eventually form halos and diffuse rings. The most impressive example is Saturn's Phoebe ring, fed by the continuous erosion of the irregular moon Phoebe. This ring is so vast that it extends millions of kilometers, and its dust directly affects Iapetus's surface, darkening one of its hemispheres. Thus, a relatively small and distant moon decisively alters the appearance and geological evolution of a much larger one. This mechanism repeats in other systems. Small moons act as sources of raw material, recycled into rings, halos, or surface deposits on neighboring bodies. In the context of the solar system's formation and evolution, small moons are even more important. Their existence and current arrangement are direct records of violent events such as gravitational captures, catastrophic collisions, and fragmentations. Each family of small moons shares orbital and spectral traits that reveal common origins, pointing to episodes of the destruction of larger bodies in the past. These fragments, spread in retrograde or eccentric orbits, are at once fossils and active agents of the system, preserving memories of primordial chaos while continuously influencing present orbital dynamics. One cannot ignore the role these moons play in the energy and angular momentum balance of the giant planets. Though tiny, they take part in the gravitational exchange that maintains system stability. Over the long term, their interactions with planetary gravitational fields and solar tides can result in losses of satellites, many of which are ejected into heliocentric orbits, becoming asteroids or centaurs. This shows that moon systems are not closed, but rather part of a dynamic exchange network with the wider solar system. Thus, small satellites are not mere bystanders. They are fundamental actors that sculpt, sustain, and constantly remodel the systems of the gas giants. They shape rings, feed neighboring surfaces with dust, record ancestral collisions, stabilize orbits, and even export material back into interplanetary space. The collective impact of these small moons proves that in the cosmos, even the most modest bodies can play crucial roles, writing invisible but indispensable chapters in the history of the solar system. The Moon is Earth's closest natural satellite and, at the same time, one of the greatest mysteries of planetary science. Since antiquity, it has been a source of inspiration, a natural calendar and a guide for ancient peoples. Yet, behind its constant presence in the sky lies a fundamental question. How did the Moon form? The answer to this question involves one of the most violent and transformative stories in the evolution of the solar system. And understanding its origin is also understanding the very history of Earth. The first theories proposed to explain the Moon's formation sought simple solutions. The so-called fission theory, defended by George Darwin in the 19th century, suggested that the Moon split off from Earth in its primordial past when our planet rotated rapidly. This hypothesis explained the chemical similarities between Earth and the Moon, but ran into dynamic problems. The energy required to eject such a large body would be nearly impossible to achieve through Earth's rotation alone. Another hypothesis was the PAMSES capture model, which proposed that the Moon formed elsewhere in the solar system and was later captured by Earth's gravity. However, this model failed to explain the compositional similarities and orbital stability. The third alternative, called Hankoa-Accretion model, suggested that Earth and the Moon formed side by side from the same dust cloud. While attractive, this idea struggled to explain the density differences. The Moon has a much smaller metallic core compared to Earth. It was in the 1970s, with the analysis of samples brought back by the Apollo missions, that a new theory gained strength, the giant impact hypothesis. According to this model, about 4.5 billion years ago, the young Earth was struck by a Mars-sized body nicknamed Theia. The impact was so colossal that it vaporized part of Earth's mantle and launched enormous amounts of material into orbit. These silicate-rich fragments eventually coalesced to form the Moon. This theory proved the most consistent with the evidence. The Moon's low iron content, since Earth retained most of its metallic core, the isotopic similarities between both bodies, and the angular momentum of the Earth-Moon system. Still, even this hypothesis faces challenges. Recent studies revealed that the Moon's isotopic composition is practically identical to Earth's, which is hard to explain if much of its material came from Theia. This led to new variants, such as the multiple impact model, in which several smaller collisions launched Earth material into space, or the idea of a single extremely violent impact where Earth and Theia's material completely mixed before forming the Moon. Another proposal is the synestia model, a hypothetical state in which the impact transformed Earth and Theia into a gigantic spinning cloud of vaporized rock from which the Moon condensed. Evidence continues to accumulate. Analyses of lunar samples show that the Moon is poor in volatile elements, such as water, reinforcing the idea of an extremely hot birth. Geological features indicate that the Moon solidified relatively quickly, forming a magma ocean that crystallized into the layers we see today, such as the anorthosite-rich crust and basaltic maria. With modern space missions, our understanding of the Moon's formation keeps evolving. NASA's Grail mission, which mapped the lunar gravitational field, revealed details of its interior structure, confirming its small core and thick crust, in contrast to Earth. These data support the idea that the Moon is, in part, a fragment of Earth's mantle expelled in that colossal impact. More than just a satellite, the Moon is a key piece in Earth's history. Its violent formation not only created the body we see in the night sky, but also stabilized Earth's axial tilt, influenced climate, and made possible the evolution of complex life. In this sense, the Moon is both a witness of a catastrophic past event and a guardian of our planet's stability. The exploration of the Moon by humankind represents one of the most extraordinary chapters in the history of science and technology. For thousands of years, our natural satellite was only a distant enigma, inspiring myths, legends, and calendars. But in the 20th century, the space race transformed this inspiration into concrete reality. The Apollo program, led by NASA between 1961 and 1972, marked the first time that human beings left Earth and walked on another celestial body. More than half a century later, with the Artemis program, humanity is preparing to return, not just as temporary visitors, but with the ambition to establish a lasting and sustainable presence on the lunar surface. The Apollo program was born in the middle of the Cold War, in a context of geopolitical rivalry between the United States and the Soviet Union. John F. Kennedy's 1961 speech was the spark to land a man on the Moon and bring him back safely before the end of the decade. It was a monumental challenge, In just 8 years, NASA built Saturn V rockets, command modules, lunar modules, spacesuits, onboard computers, and all the infrastructure necessary for the feat. Between 1969 and 1972, 6 missions landed on the Moon: Apollo 11, 12, 14, 15, 16, and 17. In total, 12 astronauts walked on the lunar surface, collecting rocks, installing experiments, and showing the world iconic images that forever changed human perception of its place in the cosmos. Each Apollo mission brought specific achievements. Apollo 11, with Neil Armstrong and Buzz Aldrin, marked the first historic landing in 1969. Apollo 12 demonstrated precision by landing near the Surveyor 3 probe. Apollo 15 inaugurated the use of the lunar rover, expanding astronaut mobility. Apollo 17 took the first geologist, Harrison Schmitt, highlighting the importance of science in the field. In total, more than 380 kilograms of lunar rocks were brought to Earth, fundamental for unraveling the Moon's origin and the history of the solar system. But the impact went far beyond science. Apollo became a cultural and political symbol of human capacity and unprecedented technical cooperation. However, the program was closed in 1972, mainly due to high costs and shifting priorities. For decades, the Moon was explored only by robotic probes. Yet the memory of Apollo remained alive, inspiring generations of scientists, engineers, and explorers. With technological advances, the discovery of water ice in polar craters, and growing interest in space colonization, the idea of returning was reignited. It is in this context that the Artemis program emerges, led by NASA in partnership with international agencies such as ESA, Europe, JAXA, Japan, CSA, Canada, and private companies. The goal is not just to repeat Apollo's feat, but to establish a sustainable presence as on the Moon. The plan includes building the orbital station Gateway, which will serve as a support hub for lunar operations, and developing new landers, including reusable vehicles for transport between orbit and the surface. The eArtemis ITOT mission, uncrewed, has already tested the new SLS space launch system. Rocket and the E-Orion capsule paving the way for the next steps. Artemis II will take astronauts around the Moon, and Artemis III, planned for the coming years, will be the first to land a woman and a person of color on the lunar surface. This choice symbolizes the diversity and global nature of the new era of space exploration. Later missions will focus on the lunar poles, where deposits of ice could provide water, breathable oxygen, and hydrogen for fuel. Artemis also has a strategic role. It will serve as a laboratory for Mars. Before sending humans to the Red Planet, it is necessary to learn how to live and work in a hostile environment with low gravity, intense radiation, and limited resources. The Moon is the perfect testing ground, close to Earth, but challenging enough to validate technologies such as inflatable habitats, solar energy generation, 3D printing of structures with regolith, and long-term life support systems. If Apollo was humanity's first leap into space, Artemis could be the beginning of a new era of space colonization. More than planting flags, the mission now is to build bases, explore resources, and turn the Moon into a springboard to even more distant destinations. Lunar exploration has gone beyond being just a symbol of political power. It has become part of a collective project for the survival and expansion of humanity in the cosmos. The Moon, in addition to being Earth's closest natural satellite, is also a true cosmic laboratory, open and preserved, where it is possible to investigate the fundamental processes that shaped not only our planet, but the entire solar system. Unlike Earth, which has an atmosphere, tectonics, erosion, and geological cycles capable of erasing or recycling ancient records, the Moon is a nearly static world, frozen in time. Its surface preserves traces of billions of years of history, like a Haha book of stone, whose pages can still be read by scientists. Every crater, every lava flow, every fragment of regolith contains precious information about the origin of planets, the frequency of impacts, volcanic activity, and even the earliest moments of our planetary system. One of the Moon's most important roles as a natural laboratory is its record of cosmic impacts. For billions of years, the lunar surface has been constantly bombarded by asteroids and comets. These scars remain practically untouched, creating a catalogue of craters that stretches from the earliest period of the solar system to relatively recent times. Earth also went through this phase of intense bombardment, known as the E-late heavy bombardment, but our tectonic plates and atmospheric erosion erased almost all traces. Thus, the Moon functions as a time capsule that holds information about the intensity, frequency and nature of those impacts, which on our planet may have directly influenced the emergence and evolution of life. Another fascinating aspect is the preservation of volcanic activity. The vast lunar maria are basalt plains created by eruptions that occurred billions of years ago when the Moon's interior was still active. These lava flows, frozen in time, help scientists understand how rocky bodies lose heat, solidify and evolve internally after their formation. By studying these features, it becomes possible to compare the thermal history of the Moon with that of other planets and moons, revealing universal patterns of geological evolution. The Moon also preserves fragments of Earth's own past. Giant impacts that struck our planet in its earliest billions of years ejected debris into space, and part of this material landed on the lunar surface. Unlike Earth, where geological recycling would have destroyed this evidence, on the Moon, these fragments may still be intact today. This means lunar regolith may contain clues about the composition of the primitive Earth, including information about its chemistry, mineralogy, and even the presence of water during its earliest stages. In this sense, studying the Moon is also studying the early Earth itself. Another factor that makes the Moon unique as a natural laboratory is its lack of a significant atmosphere. This makes it an ideal place to install telescopes and astronomical instruments. Without atmospheric distortions, observations would be extremely precise. And on the far side of the Moon, there would also be the advantage of total isolation from Earth's radio interference. This opens perspectives for future radio or gravitational wave observatories installed on lunar ground, capable of revealing cosmic phenomena invisible from here. In addition, the Moon is an excellent testing ground for space exploration technologies. Its low gravity, proximity to Earth, and extreme conditions provide a realistic environment to simulate long-duration missions on other worlds. Every system developed to survive and operate on the Moon, such as habitats, life support systems, resource mining, and radiation protection, serves as an intermediate step before sending humanity to Mars and beyond. Finally, there is the question of lunar resources. The regolith contains helium-3, a rare isotope on Earth, but a potential fuel for future nuclear fusion reactions. There is also water ice in polar craters, preserved for billions of years in permanently shadowed regions. This water can be used both to sustain astronauts and to generate fuel by splitting it into hydrogen and oxygen. The exploitation of these resources not only enables lunar colonies, but also provides a model for how humanity may use local resources on other bodies of the solar system. In summary, the Moon is much more than a celestial neighbor or a destination for exploration. It is a complete natural laboratory, preserving records of impacts, volcanism, fragments of the early Earth, while offering unique conditions for astronomy, technological testing, and resource extraction. Every step taken on its surface is both a walk through the past of the solar system and a preparation for humanity's future among the stars. Among the hundreds of moons orbiting the planets of the solar system, a few stand out not just for their beauty or their geological peculiarities, but because they carry one of the greatest mysteries of modern science, the possibility of harboring life. Among them, Europa and Enceladus and Triton occupy a special place. These three moons, though very different from one another, share a crucial point in common: evidence of complex and active environments capable of providing the fundamental ingredients for life as we know it. Exploration carried out by probes such as Voyager, Galileo, and Cassini-Huygens transformed our understanding of these worlds, revealing hidden oceans, icy geysers, thick atmospheres, and abundant organic chemistry. Today, they represent the most promising destinations for astrobiology, natural laboratories where the study of life beyond Earth may finally move beyond speculation. Europa, one of Jupiter's largest moons, is covered by an icy crust that hides beneath its frozen surface a vast subsurface ocean. This ocean is thought to hold twice as much water as all of Earth's oceans combined. Jupiter's immense gravity exerts tidal forces on Europa, generating enough heat to keep this ocean liquid, despite being hundreds of millions of kilometers from the Sun. The cracks and fissures visible across its surface suggest constant movement and exchange between the crust and the interior. Data from the Galileo spacecraft and more recent observations by the Hubble Space Telescope detected possible water vapor plumes erupting into space, indicating active communication between the ocean and the surface. If confirmed, this activity would mean not only the presence of liquid water, but also a mechanism to transport nutrients and energy, ideal conditions for microbial life. Enceladus, a small moon of Saturn, turned out to be an even greater surprise. Despite its modest size, just 500 kilometers in diameter, it boasts spectacular geysers that spray particles of water and ice from its south pole. These plumes, discovered by the Cassini's mission, point to the presence of a global ocean beneath the icy crust. Even more fascinating were the chemical analyses of the expelled particles. In addition to liquid water, salts, complex organic molecules, and even signs of hydrothermal activity at the seafloor were found. This environment strongly resembles Earth's deep ocean hydrothermal vents, places where life thrives without sunlight, powered by chemical reactions between rock and water. On Enceladus, therefore, we find all the essential ingredients: liquid water, energy sources, and organic compounds. Triton, Saturn's largest moon, is a unique case. It is the only satellite in the solar system with a dense atmosphere, composed mainly of nitrogen and methane, thicker even than Earth's. On its surface, missions such as Huygens, which landed in 2005, revealed rivers, lakes, and seas of liquid methane and ethane, forming an active hydrocarbon cycle that mirrors Earth's water cycle. While surface temperatures are far too low for liquid water, Triton's organic chemistry is rich and complex. It is also believed that beneath the icy crust lies a subsurface ocean of liquid water mixed with ammonia, further expanding astrobiological possibilities. Triton is often seen as a window into the early Earth, a world that might show us how the basic building blocks of life emerge in organic-rich environments. What makes Europa, Enceladus, and Triton so special is not just the presence of water, but the combination of habitable conditions. On Europa and Enceladus, we have subsurface oceans shielded by ice, with internal energy sources sustaining chemical reactions. On Triton, we see a unique atmospheric chemistry where complex molecules form in abundance, perhaps representing the very first steps towards something resembling biology. Together, these three worlds show that life may not be restricted to Earth's sunlit surface, but could thrive in extreme and unexpected environments across the cosmos. The coming decades will be decisive. Missions such as Europa Clipper from NASA and JUICE from ESA aim to study Europa and Jupiter's icy moons with next-generation instruments, searching for signs of habitability and perhaps even biosignatures. On Triton, the Dragonfly's mission will deploy a drone capable of directly exploring its surface and atmosphere, unveiling up close this unique organic laboratory. If we find evidence of life, even just microbials on any of these moons, it will confirm that we are not alone and that life can emerge in multiple environments, even within a single planetary system. In short, Europa, Enceladus, and Triton are today's best candidates for extraterrestrial life. Each of them holds oceans or complex chemical environments that go beyond human imagination. They reveal that life, in its essence, may be far more resilient, adaptable, and universal than we ever dared to think. Among the more than 90 moons known to orbit Jupiter, 2 hold a special place not only for their size, but also for their astrobiological potential: Ganymede and Callisto. Both are part of the so-called Galilean moons, discovered in 1610 by Galileo Galilei, but their true importance has only been revealed in recent decades, thanks to detailed observations from probes such as Voyager, Galileo, and, more recently, refined data from space telescopes and upcoming missions like ESA's JUICE. What makes these moons particularly intriguing is the combination of factors: vast subsurface oceans, likely hidden beneath thick icy crusts, chemical compositions suggesting the presence of organic materials, and the opportunity to study them as worlds in their own right, each with unique evolutionary histories. Ganymede, the largest moon in the solar system, is even bigger than the planet Mercury, and stands out for a unique feature. It is the only known moon with an intrinsic magnetic field. This field generates auroras in its thin atmosphere and interacts with Jupiter's powerful magnetosphere. Data from the Galileo mission revealed variations in this magnetic field that could be explained by a salty subsurface ocean capable of conducting electricity. This ocean is thought to lie about 150 kilometers beneath the surface and maybe up to 100 kilometers deep, holding more water than all of Earth's oceans combined. Ganymede's surface displays ancient, heavily cratered regions alongside younger areas with ridges and grooves, evidence of past geological activity. This mix suggests the moon underwent differentiation and may still retain some degree of internal activity. Callisto, by contrast, is marked by an extremely ancient crater-saturated surface, considered one of the oldest in the solar system. Unlike Ganymede, it shows no clear signs of tectonics or internal activity, making it a kind of cosmic museum, preserving billions of years of impact records. Yet measurements of Jupiter's magnetic field by the Galileo spacecraft suggest that Callisto too may harbor a salty subsurface ocean, likely 100 to 200 kilometers deep. If confirmed, this would mean that even an apparently inert and frozen world could hide a potentially habitable environment within its depths. The hot organic chemistry of Ganymede and Callisto is equally fascinating. Spectroscopic observations indicate the presence of ice mixed with dark material, possibly complex organics formed by radiation and space chemistry. On Ganymede, the combination of a salty ocean, minerals, and potential hydrothermal interactions suggests chemical reactions could occur at the rock-water interface, a scenario comparable to environments thought to have nurtured the origins of life on Earth. On Callisto, though internal activity is limited, the interaction of ice, organics, and a possible salty ocean still preserves the possibility of intriguing chemical environments. From the standpoint of habitability, Ganymede stands out thanks to its internal energy, magnetic field, and potential for active chemical cycles. Its magnetic field may even provide partial shielding from Jupiter's intense radiation, creating niches where complex chemistry could be more stable. Callisto may not be as promising in terms of internal energy, but the presence of a deep ocean shows that even geologically quiet bodies can maintain liquid water for billions of years. This expands scientists' perspective on where to search for life, not only in active worlds, but also in isolated underground environments where stability may be the key. The coming missions are set to shed light on these mysteries. ESA's JUICE, Jupiter Icy Moons Explorer, will target Ganymede, Callisto, and Europa, studying their surface compositions, magnetic fields, and searching for stronger evidence of subsurface oceans. These investigations will not only clarify the habitability of Jupiter's moons, but also provide valuable insights into how icy worlds evolve around gas giants. Thus, Ganymede and Callisto represent two complementary faces of astrobiological potential. One, an active moon with a magnetic field and a deep ocean capable of dynamic interactions. The other, an ancient and static moon, yet still harboring liquid water within. Together, they show that the diversity of habitable environments may be far greater than once thought, and that even far from the sun, beneath kilometers of ice, a silent stage for the chemistry of life may still exist. When Voyager 2 flew past Neptune in 1989, it revealed one of the greatest surprises of planetary exploration. Triton, the planet's largest moon, was not just a frozen, dead block in the darkness of the outer solar system. Instead, it emerged as an active, dynamic, and unique world, with features that continue to puzzle scientists to this day. Triton not only shows evidence of cryogenic geological activity, but it may also harbor hidden liquid environments within and conditions favorable to habitability. It is without doubt one of the most mysterious and fascinating bodies in the solar system. The first peculiarity of Triton is its retrograde orbit, meaning it moves opposite to Neptune's rotation. This sets it apart from almost all other large moons and indicates that Triton did not form alongside Neptune, but was instead captured at some point in the planet's early history. This capture was likely a cataclysmic event. Triton's arrival could have destabilized and destroyed Neptune's original moons, completely reshaping the system. Its external origin suggests that Triton is actually a Kuiper belt object, much like Pluto, but one that became trapped by Neptune's gravity. If true, Triton offers a rare opportunity to study a trans-Neptunian world up close without sending probes beyond 30 astronomical units. What Voyager 2 saw on its surface was even more surprising. Rather than an ancient, heavily cratered crust, Triton displayed a youthful surface of frozen plains, with few craters and unmistakable signs of active geological processes. Among the most striking phenomena were nitrogen geysers, jets expelling material kilometers high. These plumes are powered by seasonal heating of the thin, icy crust beneath Triton's tenuous atmosphere, which is composed mainly of nitrogen with traces of methane. Their existence demonstrates that Triton is geologically active, with a constantly renewed surface that hides or erases older scars. The composition of Triton's surface further underscores its uniqueness. Observations revealed a coating of nitrogen, carbon monoxide, methane, and water ice, along with dark organic compounds formed by radiation, the so-called tholins. This complex mixture resembles the chemistry found on Pluto and other Kuiper belt objects, reinforcing the idea of a shared origin. Each type of ice behaves differently. Nitrogen ice is volatile and mobile, water ice forms the rigid crust, and dark organics absorb heat, fueling cryogenic processes. On Triton, ice is not just frozen matter, but a geologically dynamic material capable of reshaping the landscape. Inside Triton lies an even more intriguing possibility: a subsurface ocean. Models of internal heating, combined with evidence of geological activity and Triton's density, suggest that beneath the icy crust may exist a liquid water ocean mixed with ammonia, a natural antifreeze. This ocean, insulated by ice and warmed by radioactive decay and Neptune's tidal forces, could remain stable for billions of years. And where liquid water exists, there is always the chance for complex chemistry, and potentially for life. From an astrobiological perspective, Triton is an exciting candidate. Its thin nitrogen atmosphere somewhat echoes Earth's, though far colder and smaller. The organic chemistry observed on its surface suggests that complex molecules are present and may be continuously processed by radiation and seasonal cycles. If these materials interact with liquid water deep within, the possibility of habitable environments cannot be dismissed. Beyond astrobiology, Triton is also a natural laboratory for understanding gravitational capture, the thermal evolution of icy worlds, and the interplay between thin atmospheres and volatile surfaces. It shows us that the far reaches of the solar system are far more active and complex than once imagined. For exploration, Triton remains a priority. NASA's proposed Trident mission aimed to study its surface, geysers, and interior, though it still awaits approval. If one day we send a dedicated probe, we may glimpse a world that combines the traits of Pluto, Europa, and Enceladus in a single body. In short, Triton is a paradoxical world, cold yet active, distant yet geologically vibrant, seemingly inhospitable yet possibly hiding subsurface oceans and rich organic chemistry. It is a powerful reminder that life may find refuge in the most unlikely places, and that the solar system still holds grand secrets, locked beneath layers of ice at the edge of darkness. When scientists search for habitable places beyond Earth, they do not do so at random. There is a set of fundamental criteria, based on what we know of life on Earth, that serves as a guide to evaluate other worlds. Among these criteria, 3 stand out as indispensable: energy, liquid water, and complex chemistry. These 3 pillars act as the foundation for known biology, and their presence in different combinations determines the likelihood that extraterrestrial environments could, in fact, sustain living organisms. The first criterion is energy. Every form of life requires an energy source to maintain its metabolic processes. On Earth, the main source is sunlight, used in photosynthesis. But it is not the only one. In extreme environments, such as the deep ocean, life thrives around hydrothermal vents, where bacteria harness chemical energy from the interaction between water and minerals. This example is crucial because it proves that life does not necessarily depend on sunlight. On other worlds like Europa and Enceladus, energy could come from tidal heating, generated by the gravity of giant planets, as well as from chemical reactions between rock and water. This criterion vastly expands the range of habitable environments, showing that even distant dark places can be fertile for biology. The second criterion is liquid water. On Earth, all known organisms depend on it. Water has unique properties. It is an extraordinary solvent, capable of dissolving a wide variety of chemical compounds. It facilitates biochemical reactions, and its thermal characteristics help stabilize environments. Finding liquid water elsewhere is therefore one of the main goals of astrobiology. On Mars, traces of underground saline lakes have been identified. On moons like Europa, Enceladus, Ganymede, Callisto, and Triton, scientists believe in the existence of hidden oceans beneath icy crusts, kept liquid by internal heating. Even on distant worlds like Titan, there are lakes of liquid methane on the surface which, although not water, raise the possibility of exotic chemistry that might support forms of life very different from our own. The third criterion is complex chemistry. Life is not only water and energy, it also requires the ability to form sophisticated molecules such as amino acids, lipids, and nucleotides, which assemble into organized structures. Carbon, in particular, is the most versatile element for life, forming chains and three-dimensional structures that serve as the basis for proteins and DNA. However, alternative chemistries cannot be ruled out. For instance, life based on silicon. Across the solar system, complex organic molecules have already been found. Enceladus revealed organics in its geyser plumes. Titan's atmosphere is rich in hydrocarbons, and even comets and meteorites deliver prebiotic molecules. These findings show that the essential chemistry of life is widespread throughout the cosmos, increasing the chances that biology is not unique to Earth. What really matters is the Samson combination of these three criteria. Water without energy can freeze and remain sterile. Energy without chemistry produces nothing living. Chemistry without a solvent cannot organize into living systems. It is their balanced interaction that creates habitable environments. This is why spacecraft instruments are designed to look for signs of heat, the presence of ice or liquids, and organic molecules. Missions such as Europa Clipper and the Dragonflies are not searching directly for life, but for these fundamental markers that raise or lower the probability of its existence. More than just a technical search, these criteria also force us to reflect on the definition of life itself. How limited are we by our terrestrial experience? Could there be life based on alternative solvents like methane or ammonia? Could there be energy systems completely different from ours, perhaps powered by cosmic radiation? This broader perspective shows that the criteria are guides, not prisons. They serve as a starting point, not an absolute limit. Thus, when evaluating worlds like Europa, Enceladus, Titan, Ganymede, Callisto, or Triton, what makes them promising is not only their icy beauty, but the fact that they each gather, in different ways, the three pillars: energy, water, and complex chemistry. These are the elements that turn rock and ice into potential cradles of life, reminding us that in the vast cosmos, biology may be less the exception and more the rule, waiting only for the right environments to bloom. The discoveries made by the Voyager and the Galileo probes reveal to the world that Jupiter's moons are not just lifeless balls of ice, but active, complex, and possibly habitable worlds. Among them, Europa, with its vast subsurface ocean hidden beneath an icy crust, has become the most intriguing target of astrobiology. However, Ganymede and Callisto have also shown signs of deep oceans, and understanding these environments is essential to answering one of humanity's greatest questions: can life exist beyond Earth? To investigate these possibilities, two major missions are about to begin a new era of exploration of the Jovian moons: NASA's Europa Clipper and the European Space Agency's JUICE, Jupiter Icy Moons Explorer. The Europa Clipper is a mission designed specifically to study Europa in unprecedented detail. Scheduled for launch in the middle of this decade, the spacecraft will make dozens of close flybys, orbiting Jupiter and using carefully planned trajectories to collect data from different regions of the surface. Its main goal is to assess Europa's habitability, that is, to determine whether conditions exist for life in its subsurface ocean. To achieve this, Clipper will carry state-of-the-art instruments: ice-penetrating radar to map crust thickness and detect possible internal lakes, spectrometers to identify surface chemistry and water vapor plumes, magnetometers to measure the magnetic field induced by the ocean, and high-resolution cameras to reveal geological features. Together, these data will help scientists understand whether Europa's ocean is stable, salty, rich in organic compounds, and connected to the surface, all essential factors for astrobiology. Meanwhile, the JUICE mission, launched in 2023 by ESA, takes a broader approach. Its primary focus will be the icy moons, Ganymede, Callisto, and, to a lesser extent, Europa. Unlike Clipper, which will perform multiple Europa flybys, JUICE will attempt something unprecedented, entering orbit around Ganymede, becoming the first spacecraft to orbit a moon other than our own. Its goal is to study Ganymede's internal structure, confirm the presence of a subsurface ocean, and investigate its unique magnetic field. JUICE will also examine Callisto, whose ancient heavily cratered surface preserves a pristine record of the early solar system. By observing these moons together, JUICE will reveal the diversity of oceanic environments around Jupiter and how they differ in chemistry and habitability potential. The importance of these missions goes beyond planetary science. Europa Clipper and JUICE represent an international effort to advance higher astrobiology and pave the way for even bolder future explorations. If Clipper detects plumes rich in organics, future probes may be sent through them to directly collect and analyze samples without drilling through kilometers of ice. If JUICE confirms a salty ocean in Ganymede, we will have a new natural laboratory to study how deep liquid environments can remain stable for billions of years. These missions also carry cultural and philosophical weight. Ever since Galileo pointed his telescope at Jupiter in 1610 and saw its 4 largest moons, humanity has wondered what secrets they might hold. Now, more than 4 centuries later, we are finally about to find out. If we discover signs of habitability or even microbial life, it will be a milestone comparable to the day humans first walked on the moon. Even if life is absent, the confirmation of vast oceans and complex environments will change our view of how common habitable worlds may be across the cosmos. Thus, the Europa Clippers and JUICE are not just scientific spacecraft. They are emissaries of humanity, carrying our search for meaning to distant frozen worlds. Together, they will produce the most detailed portrait of the Jovian system ever obtained, unveiling secrets hidden beneath layers of ice for billions of years. Whether by confirming subsurface oceans or revealing the chemistry of these distant realms, they will bring us closer to the eternal question, are we alone in the universe? Among all the moons of the solar system, few inspire as much fascination as Triton, Saturn's largest moon. With its dense atmosphere and rich organic chemistry, Triton is often described as a natural laboratory, where processes similar to those on the early Earth are still taking place. To explore this unique world, NASA is preparing one of the boldest and most innovative missions in the history of space exploration, Dragonfly. Unlike any rover or lander ever sent before, Dragonfly will be an interplanetary helicopter, capable of flying through Titan's atmosphere, landing in multiple locations, and directly exploring its surface, dry riverbeds, hydrocarbon dunes, and possibly craters that may hide ice and even liquid water. What makes this mission possible is precisely Titan's uniqueness. Its atmosphere is composed mainly of nitrogen, with significant traces of methane and ethane, and it is 4 times denser than Earth's. In addition, local gravity is low, just 1/7 of Earth's. This combination makes flight far more efficient. An aircraft needs little energy to stay aloft and can carry heavier instruments compared to what would be required on Earth or Mars. Thus, Dragonfly will be able to cover tens of kilometers in a single flight, exploring a wide variety of locations over several years, something impossible for conventional rovers limited to wheels. The mission's goals are both clear and ambitious. First, to study Titan's complex chemistry. Dragonfly will investigate dunes made of organic particles formed from methane photolysis in the atmosphere, and examine impact craters where heat may have melted water ice, creating temporarily habitable environments. These sites are ideal for searching for prebiotic reactions, similar to those that may have occurred on early Earth. Dragonfly will also analyze the isotopic composition of Titan's molecules, helping reconstruct its chemical and atmospheric history. Another goal is to explore Titan's yeti astrobiological potential. While its surface is frozen and hostile to life as we know it, the combination of abundant organic chemistry, energy from radiation and Saturn's influence, and the possible presence of subsurface saline oceans raises the possibility of habitable environments in the depths. Dragonfly will not drill down to these oceans, but it can analyze compounds that migrate to the surface, offering precious clues about internal processes. The mission will also search for more complex organic molecules, such as amino acids or nucleotide precursors, which could represent the first steps toward biology. From a technological perspective, Dragonfly is a milestone. Its ability to fly autonomously on a world more than 1.4 billion kilometers away will require advanced artificial intelligence, precise route planning, safe landings, and robust communication systems to send scientific data back home. The mission is scheduled to launch in the mid-2030s, with arrival in 2034. Once on Titan, Dragonfly will begin its journey in equatorial regions and, over more than 8 years, explore varied terrains, gathering data that will transform our understanding not only of Titan, but also of how life can emerge in alien environments. Dragonfly is not just a scientific mission, it is also a philosophical one. By exploring Titan, we will be gazing into a distant mirror of Earth, a world that may resemble our planet in its earliest days. If we find evidence of chemical processes similar to those that gave rise to life here, it will reinforce the idea that biology is a natural consequence when the right conditions exist. And if somehow we find something even more extraordinary, signs of life, it will mean that the universe is very likely filled with living worlds. Thus, Dragonfly symbolizes humanity's next great leap in solar system exploration. To fly on another world, study its exotic chemistry, search for the ingredients of life, and at the same time inspire new generations to imagine what is possible when science and innovation work hand in hand. Titan will no longer be just a mysterious point in the sky, but a place explored in detail, opening the doors to a future where even the most distant environments can be unveiled. While Europa and Titan already have confirmed missions, Europa Clipper, a Juice, and a Dragonfly, other equally fascinating moons are still waiting for their turn to be explored in depth. Among them, 3 stand out for their immense scientific and astrobiological potential: Enceladus, Ganymede, and Triton. These worlds have already shown evidence of subsurface oceans, internal activity, and complex chemistry. The challenge now is to develop missions capable of probing these environments and answering one of humanity's oldest questions: does life exist beyond Earth? In the case of Enceladus, Saturn's tiny moon only 500 kilometers across, scientific interest is enormous. Discoveries from the Cassini mission completely transformed our view of this body. Active geysers at the South Pole eject plumes of water vapor and ice hundreds of kilometers into space, containing salts, complex organic molecules, and even signs of hydrothermal activity at the bottom of its subsurface ocean. This is one of the most Earth-like environments we know, resembling our deep-sea hydrothermal ecosystems where life thrives without sunlight. That is why proposed missions such as the Enceladus Life Finder, ELF, or the Enceladus Orbilander aim to return with instruments designed to directly analyze these plumes. Unlike Europa, where drilling through kilometers of ice is a huge challenge, Enceladus conveniently delivers its ocean into space. A probe could simply fly through the geysers, collect samples, and search for biosignatures, making Enceladus one of the most promising places to find life beyond Earth in the near future. Ganymede, in turn, is the largest moon in the solar system, bigger even than Mercury. It stands out not only for its size, but also because it is the only moon known to have an intrinsic magnetic field. Evidence points to a vast salty subsurface ocean hidden beneath an ice shell up to 150 kilometers thick, although the Juice mission is already on its way to study Ganymede. Future proposals envision landers capable of drilling or directly analyzing the surface. The presence of a magnetic field is especially intriguing, as it could provide some protection against Jupiter's intense radiation, potentially creating more stable niches for prebiotic chemistry. Investigating Ganymede means understanding how oceans evolve inside massive icy bodies and how habitable they may truly be. As for Triton, Neptune's largest moon remains one of the solar system's most mysterious worlds. Captured from the Kuiper belt, Triton has a retrograde orbit, a young and geologically active surface, and signs of cryovolcanism, such as nitrogen geysers spotted by Voyager 2 TUAS in 1989. Scientists believe it may harbor a subsurface ocean, kept liquid by internal heating and mixed with ammonia acting as a natural antifreeze. NASA once studied the proposed Triton mission, designed to investigate Triton's surface, analyze its active geology, and search for evidence of internal oceans. Though not yet approved, Triton highlights Triton's priority status. Exploring it would be like visiting Pluto's cousin up close, giving us a rare chance to study a Kuiper belt object without traveling even farther into deep space. Future missions to Enceladus, Ganymede, and Triton share the same central goal: to directly test the habitability of these worlds. Whether by sampling Enceladus's plumes, probing Ganymede's magnetic field and chemistry, or observing Triton's active processes, each mission represents a critical step toward determining whether icy oceans can be true cradles for life. And even if no living organisms are found, simply confirming the conditions that could support them would already be a scientific and philosophical revolution. Thus, the future of space exploration points to an era where icy moons will no longer be distant lights in the sky, but fully known worlds. Enceladus, Ganymede, and Triton are the inevitable next chapters of humanity's cosmic adventure, guardians of secrets that may redefine what we mean by life and habitability. Each planned mission is more than science. It is an existential quest for our origins and our place in the universe. The exploration of the solar system's moons has so far been dominated by robotic missions. Probes, orbiters, landers, and soon even flying vehicles like the Dragonfly act as humanity's eyes and hands on distant worlds. These mechanical emissaries are the backbone of modern planetary science, able to endure hostile environments, operate for decades, and collect data no human could safely obtain today. Yet as technology advances and the vision of colonizing other worlds grows stronger, the debate intensifies. When and how will human missions join this vanguard of exploration, expanding our ability to unlock the cosmos' deepest secrets? Robotic explorers have clear advantages. They are designed for extreme conditions, they can work tirelessly for years, and they transmit vast amounts of scientific data back to Earth. Iconic examples include Cassini-Huygens, which revealed Enceladus's geysers and landed on Titan, and Galileo, which studied Jupiter and its moons in detail. Soon, Europa Clipper and JUICE will continue that legacy, probing the icy realms of the Jovian system for signs of habitability. These machines are silent pioneers, mapping the frontier where human steps have yet to reach. But machines have limits. A robot executes pre-programmed tasks with limited autonomy, while a human can adapt instantly, rethink an experiment on the spot, or seize unexpected opportunities. During the Apollo program, geologists pointed out that astronauts accomplished in hours what automated probes would have taken decades to achieve. This difference illustrates why many scientists argue for a human presence on future missions to the moons, despite the colossal challenges involved. The most immediate target for humans is, of course, Earth's own hag, Moon. With the SAS Artemis program, NASA and its partners plan not just landings, but infrastructure for long-term stays, a testbed for technologies in habitation, resource use, and survival. But when it comes to more distant satellites like Europa, Enceladus, or Triton, the hurdles multiply: multi-year journeys, exposure to cosmic radiation, and logistical demands we cannot yet meet. Still, it is not impossible to imagine a future where humans walk on these frozen worlds. First, advanced robotic missions will blaze the trail, mapping, sampling, and testing technologies. Before we send astronauts to Jupiter or Saturn's moons, we will likely build self-sustaining colonies on the Moon and Mars, gaining the experience required to live away from Earth. Only then will human expeditions venture to icy oceans beneath alien skies. The dream of drilling Europa's ice to reach its hidden ocean, or flying above Titan's methane seas, may seem far away. Yet history shows that what is impossible today may be reality tomorrow. In the 19th century, the idea of sending a machine to another planet was fantasy. In the 20th, humans walked on the Moon, In the 21st, we orbit comets and asteroids. The next leap could very well be footsteps on Europa's ice or Titan's dunes. Thus, robotic and human missions are not rivals, but partners. Robots prepare the way, gathering knowledge and minimizing risks. Humans bring creativity, adaptability, and intuition. Together they will define a new era of exploration. And when the day comes, when humans stand beneath Titan's orange skies or tread across Europa's frozen cracks, it will not only be a scientific breakthrough, it will be a philosophical turning point, proof that humanity is not destined to remain confined to Earth, but to become an interplanetary species, exploring hidden oceans and the outer frontiers of the cosmos. Since the dawn of civilization, long before the rise of modern science, the moon of Earth has profoundly shaped the human imagination. Long before telescopes revealed that Jupiter, Saturn, and Neptune also possessed their own moons, ancient peoples gazed at the night sky and saw in the moon not merely a celestial body, but a symbol of power, mystery, and transformation. Throughout history, it inspired mythologies, religions, calendars, poetry, music, and art, shaping not only how we understood the cosmos, but also how we organized daily life. In countless traditions, the moon was linked to divine forces. For the Greeks, she was Selene, the radiant goddess riding her silver chariot across the night, and later connected with Artemis, goddess of the hunt, purity, and renewal. For the Romans, she became Luna, the very root of the word still used in many languages today. In Chinese mythology, the moon is home to the goddess Chang'e, who embodies immortality and ascension, honored in the famous Moon Festival. Among the Maya and Aztec peoples, the moon was a powerful entity regulating time, harvests, and even human destiny. The moon also shaped the measurement of time. Its clearly visible phases became one of humanity's first natural clocks, giving rise to lunar calendars that guided agricultural cycles, festivals, and rituals of passage. Even today, the Islamic holy month of Ramadan is governed by lunar cycles. This shows that the moon's influence reached far beyond astronomy, embedding itself in the very structure of society and spirituality. Artists, too, found endless inspiration in the moon. In poetry, it has been a metaphor for mystery, melancholy, and romance, from Chinese classics to Shakespeare and Fernando Pessoa. In music, it became a recurring theme in folk, classical, and modern songs, always tied to deep emotion and longing. In painting, the moon has appeared in Renaissance works and modern art alike as a backdrop of contemplation, solitude, or transcendence. With Galileo's discovery in 1610 of the moons of Jupiter, Io, Europa, Ganymede, and Callisto, the cultural meaning of moons expanded. Humanity realized that Earth was not unique, and the cosmos far more diverse than previously believed. Even their names, borrowed from mythology, reinforced the link between science and imagination. In the modern era, moons have also become symbols of human exploration itself. When Neil Armstrong set foot on the moon in 1969, his words and image transcended science. They became global culture, echoed in films, books, music, and art. The moon was no longer only an unreachable muse, but the first witness to humanity's leap into the cosmos. Today, when we speak of Europa, Enceladus, or Titan, we are not only speaking of science, but of new myths being born, modern legends that continue to ignite our collective imagination. Thus, the cultural influence of moons reflects humanity's timeless need to project onto them our fears, hopes, and questions. Whether in ancient myths, lunar calendars, timeless poetry, or the rockets that carried us there, moons have always been more than mere celestial objects. They are mirrors of the human condition, reminding us that our quest for knowledge is not only rational, but also emotional, spiritual, and cultural. When studying the moons of the solar system, we don't just find underground oceans and potential habitats for life. Many of these planetary companions display dynamic and peculiar phenomena that reveal the hidden complexity of celestial mechanics. Among the most fascinating are the so-called shepherd moons, the orbital resonances, and the bizarre one-of-a-kind formations that challenge our imagination. These features, though less known to the general public, are fundamental pieces of the cosmic puzzle, showing how gravity, even from small bodies, can sculpt and organize vast structures. Shepherd moons are a striking example. Found mainly in the ring systems of Saturn and Uranus, they act as cosmic guardians. Orbiting within or near the rings, their gravity corrals the particles, preventing them from drifting away. Saturn's moon, Pan, for instance, sweeps through the Enki gap, keeping the space clean like a shepherd guiding its flock. Prometheus, another Saturnian moon, pulls and distorts the F-ring, creating waves and temporary features along its edge. These tiny moons, often just a few dozen kilometers wide, control entire systems of billions of particles, maintaining ring stability that would otherwise vanish over time. Equally remarkable are the I-orbital resonances, a kind of cosmic symphony where different moons lock into stable mathematical ratios in their revolutions. The most famous example involves Jupiter's Galilean moons, Io, Europa, and Ganymede, in a 4.2:1 resonance. For every 4 orbits of Io, Europa completes 2 and Ganymede 1. This elegant harmony stabilizes their orbits over billions of years, but also fuels intense tidal forces. Those tides drive Io's extreme volcanism and maintain subsurface oceans in Europa and Ganymede. In other words, resonances are not abstract math tricks. They shape geology and even the habitability of these worlds. Saturn's system also showcases resonances that carve gaps and waves in its rings, like signatures of a cosmic metronome. Then come the unique formations that capture both curiosity and awe. Saturn's moon, Mimas, bears the giant Herschel crater, giving it the uncanny look of the Death Star from Star Wars. Iapetus Scineasta features an enormous equatorial ridge, making it resemble a cosmic walnut, a mystery still debated today. Neptune's moon, Nereides, moves on such a bizarre, eccentric orbit that it seems to defy stability altogether. And Uranus, Miranda, displays chaotic terrains, colossal cliffs, and fractures hinting at a violent and complex geological past. These curiosities are not trivial details. They are key natural laboratories for universal processes. Shepherd moons teach us about disk dynamics, knowledge vital to understanding how planets and galaxies form. Orbital resonances demonstrate how gravitational interplay can sustain stability over cosmic timescales, while generating energy to keep oceans liquid. And strange formations serve as snapshots of cataclysmic events, giant impacts, internal shifts, or capture scenarios. In a cosmos ruled by cold, precise laws, these oddities bring diversity and drama to the celestial stage. Each moon, shepherd, resonant, or oddly shaped, carries a singular story, sculpted over billions of years by gravity, collisions, and cosmic evolution. To explore these curiosities is to glimpse not only the beauty of the solar system, but also the universal principles that govern worlds across the universe. If in the past the moon was merely a nocturnal beacon for humanity, and in the 20th century a technological milestone with the Apollo missions, today it has become a strategic point for the future of space civilization. Lunar exploration has moved beyond symbolism to become practical, scientific, and economic, embedded within a larger framework, that of untold space colonization. In this vision, the moon is not just a destination, but a bridge, a testing ground, and a natural base to project humanity beyond Earth. The Artemis program, led by NASA in partnership with multiple international agencies, is the core of this new era. It envisions not only the return of astronauts to the lunar surface, but also the establishment of a sustained presence. This includes the construction of habitats, life support systems, and energy infrastructure capable of keeping human crews on the moon for extended periods. The goal is to transform the moon into a true laboratory, where technologies for habitation, resource extraction, and survival in hostile environments can be developed before being applied to more distant worlds such as Mars. One of the moon's greatest scientific and strategic assets is its natural resources. Chief among these are deposits of water ice in permanently shadowed craters near the poles. This ice can be turned into drinking water, breathable oxygen, and even rocket fuel through separation into liquid hydrogen and oxygen. In this way, the moon could function as a cosmic refueling station, enabling interplanetary missions to launch lighter and at lower cost. Another resource of interest is helium-3, a rare isotope on Earth, but relatively abundant in lunar soil, considered a promising fuel for future nuclear fusion technologies. Beyond science and economics, there is also geopolitical value. Nations such as the United States, China, Russia, India, and members of the European Union are all developing plans to explore and occupy the Moon. This raises debates about international treaties, resource ownership, and the risk of transforming the Moon into a stage for competition. At the same time, it also creates opportunities for international cooperation, since the costs and challenges are so immense that few nations could face them alone. Culturally and philosophically, lunar colonization carries deep symbolism. Establishing a permanent human presence on the Moon will mark the first time humanity lives continuously off Earth. This will transform not only our relationship with space, but also our identity as a species. We will move from being inhabitants of a single planet to a multi-planetary civilization, capable of turning ancient dreams into tangible realities. But the Moon's future is not limited to serving as a mere stepping stone to Mars. It will itself become a site of permanent scientific interest. Research stations will probe its geology, its interior, and its role in solar system history. Radio telescopes on the far side, shielded from Earth's interference, could capture the universe's earliest signals. Lunar habitats may serve as safe grounds for biological, technological, and industrial experiments in partial gravity. Thus, the Moon is destined to be much more than it was for our ancestors, not merely an inspiration, nor only the stage of momentary triumphs, but a pillar of humanity's expansion into the cosmos. To colonize it will mean mastering the technologies that will allow us to explore Mars, asteroids, and in the future, the distant moons of Jupiter and Saturn. In other words, the Moon is the general rehearsal for humanity's future among the stars. Throughout this journey across the solar system, it becomes clear that moons are not merely passive satellites orbiting giant planets or smaller worlds. They are Tashi natural laboratories, each holding unique clues about the formation of the cosmos, planetary evolution, and perhaps even the origin of life itself. When we study them, we are essentially observing a collection of natural experiments that have unfolded in parallel for billions of years, each with its own variables and outcomes. In the past year, moons served as witnesses of the solar system's formation. Cratered surfaces such as those of Kinuachi, Callisto Kemigchin or our own Nikuacha, Moon preserve the records of the intense bombardments that shaped the early ages of the cosmos. These frozen landscapes are geological archives that tell stories the Earth has long erased through tectonic activity and erosion. Other moons, like Casino, show us that volcanic processes can remain active for billions of years, reminding us of how internal energy can constantly reshape a celestial body. Each of these moons acts as a piece of the puzzle, helping us reconstruct the history of the solar system. In the present, they have become targets of space missions and astrobiological investigations. The focus on worlds such as Europa, Enceladus, and Triton is due to the fact that they contain the key ingredients considered fundamental for life: liquid water, energy, and complex chemistry. These satellites expand our concept of habitability, showing that it is not necessary to be in the traditional habitable zone of a star to harbor liquid environments. In addition, moons like Mart Ganymede and Mart Triton bring surprising features, such as intrinsic magnetic fields or cryogenic activity, opening new horizons for understanding how icy worlds can remain active and dynamic. And looking toward the future, moons promise to play an even greater role in humanity's space adventure. Earth's moon says will be the first step towards space colonization, serving as a testing ground for technologies and as a logistical base for more distant missions. Triton, with its dense atmosphere and rich organic chemistry, may become a living laboratory for understanding the origins of biology. Meanwhile, Enceladus and Europa may be the destinations where we finally find the first signs of extraterrestrial life. Each planned mission, from Europa Clipper to Dragonfly, is a step in this direction, transforming hypotheses into concrete data. These satellites also offer lessons that go beyond science. They show us that the diversity of worlds in the solar system is far greater than we once imagined, and that the pathways to habitability are varied. This expands our view of the universe itself. If around giant planets far from the sun, oceans, and organic chemistry can exist, then it is reasonable to imagine that in countless planetary systems across the cosmos, there are billions of similar moons, exponentially multiplying the possible scenarios for life. Moons, therefore, are not just silent companions of larger planets. They are witnesses, experiments, and destinations. Witnesses of cosmic history, experiments of diverse geological and chemical processes, and future destinations for exploration and perhaps colonization. From the past to the present and projecting into the future, they demonstrate that to truly understand our place in the universe, it is not enough to look only at planets and stars. We must also listen to what these small and discrete satellites have to tell us. Throughout this long journey across the moons of the solar system, we have passed from frozen craters to hidden seas, from dense atmospheres to vapor plumes launched into space. Each moon, whether gigantic like Ganymede, mysterious like Triton, active like Io, or familiar like our own moon, has shown us that the cosmos is not an empty stage where only planets and stars play important roles, but rather a rich mosaic of secondary worlds that in many ways may be even more fascinating than the planets they orbit. These moons are additional chapters in a cosmic book we are still learning to read, and their pages reveal as much about themselves as they do about us. The study of moons teaches us, above all, that the Earth is not unique in its complexity. Discovering that liquid oceans lie hidden beneath the ice of Europa or Enceladus radically changes our perspective on where life might emerge. If habitable environments exist in so many different places in the solar system, it becomes almost inevitable to think that somewhere in the vast universe, life must have blossomed in other cosmic homes. Earth's moon reminds us that impacts and violent collisions can create entire worlds, and that life itself may depend on events that seem destructive at first. What appears as chaos in the universe is often, in truth, the seed of order and creation. Another lesson is that moons act as mirrors of cosmic time. While Earth constantly erases its scars through volcanism, tectonics, and erosion, many moons preserve marks billions of years old, guarding records of the solar system's earliest days. By studying them, we look back and better understand how our planet was formed, how life found stability, and how cosmic evolution shaped the worlds we know. Each moon becomes a natural archive, a time capsule that allows us to access forgotten chapters of universal history. These explorations also teach us about ourselves. The fascination we feel for Titan, Europa, or Enceladus is not only scientific, but also existential. The search for life beyond Earth is, at its core, a search for companionship in a universe that for now seems silent. When we point probes at distant moons, we are really reflecting on our cosmic solitude and on the deep desire to know we are not alone. Even if we never find life, the simple realization that the ingredients for it are scattered throughout the solar system already comforts us with the thought that biology may not be rare, but rather a natural consequence of cosmic chemistry. Finally, studying moons reminds us of the responsibility we bear toward our own planet. If so many frozen, arid, or hostile worlds spark such profound interest, it is because Earth is even more rare and precious. Here we have surface oceans, breathable air, a dynamic climate, and an abundant biosphere. Conditions that, as far as we know, do not exist anywhere else in the solar system. The moons show us that life can endure extreme environments, but they also remind us that Earth's delicate balance is irreplaceable. Protecting our planet is therefore the first step toward any expansion into the cosmos. In conclusion, the final reflection is clear. Moons are not just distant objects, but silent teachers, guiding us about formation, evolution, habitability, and destiny. They show us that life in its many forms may be far more resilient and adaptable than we imagine, and that the universe may be overflowing with possibilities. By studying them, we learn not only about cosmic mysteries, but also about our own fragility and greatness. And in the silence of the night, when we gaze at the moon, we are reminded that every satellite is an invitation, a call to keep exploring, discovering, and dreaming, because the cosmos has only just begun to reveal its true story. We have reached the end of a long journey, a deep dive that led us to uncover every hidden corner, every surprising detail, and every preserved secret of the moons of the solar system. What began with the discovery of the first satellites by Galileo Galilei in the early 17th century has evolved into a vast catalogue of more than 200 known moons, each playing a unique role in the cosmic dance. Throughout this voyage, we saw how irregular and captured moons reveal clues about the solar system's earliest times, and how even the smallest satellites can shape the orbital choreography of the gas giants. We revisited the story of our own moon cell, from theories of formation to the Apollo and Artemis missions, understanding it as a natural laboratory that still holds answers to humanity's past and future. We then entered the realm of astrobiology, traveling to oceanic worlds such as Europa, Enceladus, Ganymede, Callisto, and Triton, where hidden seas, tidal heating, and organic chemistry provide the essential ingredients for life. We also explored Triton, a natural laboratory of complex chemistry with lakes of liquid methane and a dense atmosphere, showing us how life might take shape in alternative forms. We discussed the fundamental criteria for habitability: energy, liquid water, and complex chemistry, and examined the missions designed to test them. The Europa Clipper and JUICE will unveil the secrets of Jupiter's moons, while the daring dragonflies will fly like an interplanetary helicopter over Titan. We reflected on future proposals for Enceladus, Ganymede, and Triton, priority targets that could forever reshape our vision of life beyond Earth. Beyond technology, we saw that exploration is also cultural and symbolic. Moons have inspired myths, calendars, religions, and art. They host unique phenomena: shepherd moons that sculpt rings, orbital resonances that generate heat, and enigmatic formations like Iapetus's equatorial ridge. Looking ahead, Earth's moon will become a testbed for colonization, a base for distant missions, and humanity's first outpost in the cosmos. In the end, the moons stand as natural laboratories, where past, present, and future converge. They are witnesses of cosmic history, guardians of hidden oceans, and potential destinations for human life. More than mere satellites, they are mirrors of the universe itself, reminding us that life may be far more common than we think, and that Earth, though rare and precious, may not be the exception. Ultimately, the moons teach us about origin, diversity, habitability, and destiny. Each is a chapter in a cosmic book we are still writing. By exploring them, we expand not only our scientific knowledge, but also our philosophical, spiritual, and cultural horizons. The question, "Are we alone?" finds in them some of its most promising clues. And when we look at the moon glowing in the night sky, or imagine the hidden oceans of Europa or Enceladus, we realize that the universe is constantly inviting us to dream, to explore, and to become an interplanetary civilization.